Yeah, I have to do. Good morning, everyone. My name is Jan van der West from Hansen University, and today I will be your host of the day for this final closing event of the Vale Interreg Northwest Europe project. The second part of that, but they'll explain much more about it later. But before we go to the different presentations, I would like to give the word to John from Trinity College to say a warm welcome, I hope.
Yes, thank you. So I'm Brian Broderick. I'm Associate Dean of Research in Trinity College, Dublin. I'd like to welcome all of you in the room and everyone online to this closing event for the WOW Interreg project. This project is close to our heart here in Trinity. We have, in the last couple of years, established a new office for biodiversity and climate action, headed up by a new vice president. And her role is to make sure that sustainability is embedded in everything that we do in the university, not just on the operational tasks, but also in our education and our research program. And in terms of research, we have a very long-standing and successful activity in environmental research, including topics which are very closely related to the subject of the WOW project. And that has been underpinned for many years, actually, by research funding, which has come directly from our Environmental Protection Agency and a research program that they run. And their projects that they ask us to tackle are very close to the type of projects that the WOW project has been involved in. We also have a track record of obtaining grants and being involved in collaboration and partnerships in European programs, under Horizon, for instance, but also in Interreg. Our university, and most of that research is conducted by researchers from the School of Engineering and the School of Natural Science. And Trinity College has very recently, in the last few years, established a new initiative called E3, which is designed to bring engineering, natural science, and computer science together to tackle global challenges. And that we're doing that both at an education level, and we have a new investment in a new building for that, so that we can have interdisciplinary education across those fields, but also research projects as well. So congratulations to all of you on successfully reaching the end of this project. And I'm sure you had a very successful and enjoyable time doing it. And I hope that those of you who are able to travel here can enjoy the rest of your stay in Trinity College Dublin. Thank you.
Thank you very much, John. And all the hurry and all the technical stuff going on here, I forgot to welcome everyone here, but also the people at home. So I already saw we have a lot of people joining via Zoom. So very warm welcome to you as well. And I also would like to say that in the Zoom session, you have a Q&A. So please also, if you have questions, post them in the Q&A. I will be following them and we will make a selection of the questions from that. And maybe also good to know, I hope we get a lot of questions, so we won't be able to answer all of them. So we will record them and we will answer them separately, and then we will share them with all the presentations that will be given today. So this meeting is recorded. So the recording will be available on the WOW link later on the WOW website, and also the presentations will be shared, so you can look them back. And then, well, it's already said, we have the ending of the project. So today, I think we have a very nice but also full program, which is in two parts. In the first part, we will look more into the use of activated biochar to remove micropollutants, and I'm very curious about the results of that part. And also after the coffee break, we will talk more about the production of BHA, so bioplastics from residual streams, and we will give an overview of everything that's been going on in this project as well. But before we go to the content of the projects, I'm very pleased that we have an introductional speaker. So he will give a keynote, which is Vale from Trent. And yeah, that's he is the carbon and circular economy architect, which I saw on your resume, which is a very nice name for a function. But yeah, that also is a challenge, I would say. And Pete has been involved in the first part of the WOW project, and we haven't seen him for a while, but it's very good to have old friends back. And I hope he will give a nice introduction about the challenges that water authorities are facing in becoming more circular. So I would like to give the word to you, Pete.
Thank you, Jasper. Yes, thanks, Jasper, and thank you all for inviting me to come along and learn from what's been going on in WOW 2. Thoroughly enjoyed being part of the first WOW project, and hopefully you'll see we're on the journey of trying to embed and implement some of the things that you've all been working on at full industrial scale, most notably cellulose recovery. But yeah, I mean, for me, as again, hopefully I'll demonstrate, it's so important, this collaboration with academia, with utilities across Europe and beyond. And hopefully, yeah, I should be able to demonstrate that although, as Jasper says, it's a big challenge, we are making strides to that necessary transition to a more circular and lower carbon way of operating. So, oh, where's it? What? Sorry, is it next? There we go. Enter. Perfect. I won't dwell on this. You know, most of you know a bit about Severn Trent because we were part of the first group. I've picked out, I suppose, a few salient points, things that we're proud of. So yeah, we're a big water company. The structure of the UK water companies is quite different, I think, to a lot of places across Europe. We're sort of regional water companies. So Severn Trent have 1,000 sewage treatment works and about 8 million customers. But we also have real plans to do better in terms of biodiversity, river health, net zero, circular economy. And a couple of things that have happened in the last year or two, we've had a 1.5 billion investment on environmental initiatives, which includes something we call our Great Big Nature Boost, where we're restoring peatland, which is obviously a fantastic carbon store, reviving 12,000 acres of land, planting 1.3 million trees, and are aiming to restore 2,000 kilometers of rivers by 2030. They're quite ambitious plans, and it's going to, yeah, and quite expensive plans too. We've also signed a triple pledge, a carbon triple pledge, to be operationally net zero by 2030. Now, I recognise that that's, you know, that the focus there is on scope 1 and scope 2 emissions, but we've also had our science-based targets approved by the Science Based Targets Initiative for scope 3 emissions in addition to scope 1 and 2. It will take us a bit longer to bring those down. And one of the things I'm going to talk a little bit more about today is our Resource Recovery and Innovation Centre testbed that we've built. That's proving a fantastic asset to allow us to accelerate the development of new technology. So in terms of innovation, so I work in Severn Trent's innovation team. My role, as Jasper kindly introduced, is carbon and circular economy. So the rather fancy architect term is really, my role is to design our innovation program for us to get to net zero and to really take full advantage of moving to a circular economy, so resource recovery of energy, materials and water itself, of course. But carbon and climate change is just one of our key pillars. There are obviously real shorter term challenges that we face at the moment in the UK, but I suspect probably a bit wider as well, around river health. There's a real focus on rivers as bathing waters now. Ever since the pandemic, people have appear to be a lot more connected to rivers and want to swim in rivers and use rivers as an amenity resource, which is right and proper and great. The UK has lots of combined sewer overflows, and so there are real challenges in how we work through that to reduce CSO activations. It's a very hot topic in the media amongst politicians at the moment. So big challenges there, but we've also got big plans around how we go about solving some of those issues. Of course, there's also clean water side, so making sure that the water's always on, it's always good to drink. So there's a program of work around that, big program of work around working with nature, biodiversity, enhancing nature. I've already mentioned river quality, but yeah, we have a number of river pledges around how we get our rivers to good status and to in an increasing number of sites to bathing water quality standard. And then finally, how we make sure in this period of challenge for a lot of people, there's an affordability crisis, how do we care for our customers, the people in our region? Right, so dropping, I suppose, focusing in now then on wastewater innovation. And why do we need, I know I'm preaching to the converted here, but why do we need to transform how we treat wastewater? So if you went on to the Severn Trent treatment works tomorrow, you'd probably find the technologies that we're using are not really that much different to you would have found 100 years ago. I remember speaking 10 years or so ago at the centenary of the activated sludge process conference that was invented in Manchester, or at least Manchester, one of the areas where the early development work was done, which was a great conference, but also a bit of a sad reflection on how slowly we move in the UK in terms of in the water sector internationally. So some great processes that we use, but they tend to be pretty energy intensive, chemical intensive, linear flow sheets that aren't really compatible with this low carbon biodiverse future that we need to face the climate emergency. So transitioning to a much more circular and low carbon neutral way definitely requires us to rethink how we treat wastewater, and clearly that's what the WOW project was all about, those wider opportunities from waste. So I guess a question reflected back to ourselves as a company, how do we encourage that necessary innovation and then act quickly to implement the change? A bit on carbon strategy, so it's definitely not a new ambition. So back in 2007, in our strategic direction statement, we talked about minimizing our carbon footprint. But it's certainly fair to say that the focus on carbon has intensified massively over the last few years. Our plan now is to get to net zero, and that's in our strategic direction statement. It's part of, bottom right, part of a UK-wide or England and Wales-wide net zero route map, where we as a sector have signed up to being operationally net zero by 2030. And of course, the reason we need to do that is because it's becoming more and more clear that the climate emergency is a huge threat. And I was at Cranfield University yesterday talking to a climate professor, and yeah, it's not that we're at 1 minute to midnight, we're probably 1 minute past, and if we don't act very, very quickly, we're in big trouble. I mean, the likelihood is we're going to have to learn to live with a much warmer world as it is. We need to make sure that the temperature change is kept within a limit that is that we're able to live with and mitigate. So yeah, massive challenge. So in terms of what our approach is to carbon, we've aligned our approach to Ofwat are our environmental regulator, and there the focus, the hierarchy is to focus on direct reduction of emissions. So we've done an awful lot of work over the last few years trying to measure our process emissions, our nitrous oxide and methane emissions, and the truth is they're a lot higher than we thought and were reporting through the UK standard methodology. We use something called the Carbon Accounting Workbook, but it's clear that those emissions are substantially higher. Luckily, we've got some good ideas, as I'll talk about in a bit more detail, on how to reduce those. We also, of course, need to replace fossil fuels. So we have very advanced plans and are rolling out electrification of our fleet in terms of cars and vans. We need to do more work on the heavy goods vehicles, hydrogen, compressed biomethane, etc. We're doing work on removing CO2. So I'm running a project where we're looking to lock up the carbon dioxide in combined heat and power exhaust, generating a precipitated calcium carbonate compound that has value, that can be used in paint and chemical industry, as example. And then if we still need to find extra carbon savings, we will look to offset, but our strategy is to use effectively internal offsets. So again, you know, the sort of WOW project could be really helpful there. So if we can recover cellulose or bioplastics and sell that into the market as a sustainable low carbon material, it might not be our direct carbon benefit, but it's an avoided carbon benefit for others. So that's a broad view of the strategy. As I say, you can't really manage what you don't measure. So we put an awful lot of focus into understanding our baseline, and the middle is the sort of latest representation. That's not to say it's the, you know, we're still the methodology for measuring process emissions is developing all the time. But you can see the big chunk of emissions are Scope 1 process emissions. And so, you know, Scope 2, we're able to generate a lot of energy ourselves. So 53%, I think, is the latest of the energy that Severn Trent as a group use is self-generated, mainly through anaerobic digestion of wastewater sludge, but also food waste. But yeah, the challenge really is, how do we reduce those process emissions? But we're leaning into that challenge by working with other utilities across the globe. So we have a partnership with Aarhus Vand in Denmark and Melbourne Water in Australia to develop the monitoring methodology and then the technologies that help us mitigate that. And I'll show a couple of those in a bit. And we're actually now moving to the sort of delivery phase. So I'll talk about our net zero hub, where we'll be converting a large urban wastewater treatment works, about 400,000 population, to a carbon neutral site. So our approach very much is to collaborate to find the answers, because we know we're not going to find the answers internally. We need to get out there, scour the world, join European projects such as this one to help find those answers. So we have quite a developed ecosystem now. It's taking quite a lot of effort. I've already talked about the net zero partnership with Aarhus Vand and Melbourne Water. We've got a World Water Innovation Forum, the likes of PUB in Singapore, Aqualia in Spain, a couple of North American utilities, South American utilities, Australian utilities are all part of, where we should knowledge share. And then they've got very strong relationships with academia. We run competitions both internally within Severn Trent and within our sort of customers to try and get ideas generated. So we're spending a lot more effort perhaps than we did historically on finding those clever ideas. So in terms of I mentioned our R2IC, our Resource Recovery and Innovation Centre. So that was something we built a couple of years ago, quite an investment to build it, but it's brilliant in that it's a plug and play facility. So we can bring technologies in to help speed up the development and do it at a scale that's pretty representative. So this is effectively the final step before you would fully implement on a live wastewater treatment plant. It's a safe place to play, if you like, because the effluent is based on a treatment works. It's a roughly 2,000 population equivalent mini works, but we can return the effluent to the head of the works for further treatment. So we've been running a number of trials over the recent last couple of years. Oops, sorry. Examples of, I'll talk a bit more about anaerobic treatment of wastewater. That's the big plant you can see at the top of the picture, an upflow anaerobic sludge blanket reactor, ultrafiltration membrane degas. But we've also done work on the Certec cellulose recovery equipment, on enhanced primary treatment. I've got a slide to talk about the development work we did with membrane aerated biofilm reactors. We're working with Suez on photocatalytic covers to destroy nitrous oxide. Most of our process emission monitoring work, the development work, has been done on this site too. So this is our main wastewater innovation site. So I said I'd just I'll give you a couple of examples of how we can work with academia technology providers to speed up the development of technology. So I think what is a really good example of when that works well, and of course they don't all work as well. There are plenty of examples where we've done quite a lot of development work, and we've not got to a point where we feel the technology is either feasible, viable economically, or desirable in terms of does it fit with our strategy. But this one does. The membrane aerated biofilm reactors, you may well know what they are. They're a hollow fiber dense membrane, and you supply air or oxygen down the lumen of the membrane, and the oxygen diffuses directly across the membrane to the bacteria. So a biofilm grow on the outside of the membrane. You can see the picture on the far right. The inside, that's a module full of these hollow fiber strands. You drop it into an existing tank. You can drop it in live, and it gives you extra treatment capacity, particularly for ammonia. And you can get ammonia treatment in unaerated zones because you control the air to the bacteria in such a way that you're not aerating the bulk liquid. So we first worked with Oxymem, who maybe I shouldn't have used this example being in Trinity College, not University College Dublin, but it came out of UCD. We worked with them, allowed them to use one of our sites to help develop the technology. Started at that very crude scale with an IBC cut out, but over the last sort of 10 years, they've done fantastically well developing the technology. It's now owned by DuPont and is now beginning to take off. Not only does it give us a potential low embodied carbon way of upgrading activated sludge plants, lower energy, so lower scope 2, but it also looks like, and this still needs to be fully proven, but that you can get lower nitrous oxide production. The mechanism still needs to be properly identified, but it might be just you've got a very stable oxic environment for the nitrifiers, and because you're in an oxic zone, if you are producing nitrous oxide, if you're producing nitrous oxide, you can degrade that in the anoxic tank. It can be uptaken by the heterotrophic denitrifiers. So yeah, nice process. The other one I just quickly talk about is anaerobic MBR. So this offers a vision for the future, I think. Energy neutral, chemical free, carbon neutral, no process emissions or minimum process emissions because you're not nitrifying, and resource recovery allows you to recover ammonia and phosphorus. So anaerobic treatment, been around for a while, used in Brazil and other in South America particularly. To get it to work in colder temperate climates is a challenge. You can intensify it by having an ultrafiltration membrane, returning all the bacteria to the reactor. And of course, that UF plant also gives you a solids-free effluent that still has the nitrogen and phosphorus in it that you can then use ion exchange, for example, to recover. So it's a way of recovering ammonia from the mainstream rather than the side stream, which is really exciting. You're not nitrifying, so you're not producing nitrous oxide. However, you do have lots of methane dissolved in the effluent because it's cold temperature. So you do need a way of extracting that dissolved methane. So we've worked with a membrane contactor technology, 3M membranes. That's the biggest challenge. I wouldn't say we've cracked that yet. And there may be other options available to do that, but that's a really exciting technology still in development. That's the flow sheet, which I've already really talked through. The biggest challenge that we're facing at the moment is high sulfate levels, which really then has an impact on COD removal. You've got sulfate reducing bacteria that are, of course, competing with the methanogens for the COD. So that's, I guess, in terms of bringing you up to date as to where we are with that technology development, that's what we've got to work through now. So the pilot scale that's mainly been done at Cranfield University shows that you can get up to 90% COD removal even at very low temperatures. We were more like 70%, and we think because of that sulfate challenge. So finally, I think I'm probably running out of time. Net zero hub. So the culmination of all this work, I guess, is to really try it at proper full industrial scale on one of our large treatment works. And that's what we're doing now. We've secured considerable sum of innovation funding, 10 million from Ofwat's Innovation Fund, and we're adding in another 20 million to convert Strongford to our net zero works. Carbon neutral by 2030 is, sorry, carbon neutral by next year is the intention. It's important to say that it's not just the Severn Trent project, it's something that the sector is supporting. So all the UK and the Irish water companies, both Northern Ireland and Irish Water, are supporting this project, as are our net zero partners. The learning is going to be shared across the sector. It's our biggest externally funded project to date, and we're now on site doing the building work with an ambitious target of getting it up and running by April 24, which is a lot quicker than most of our engineering projects. In terms of a bit of detail about what's going to go on there, cellulose recovery. So that's really exciting. So obviously we learned from WOW and Smart Plant, another European project all about cellulose recovery, Dutch technologies from Certec. That's at the front end of the plant. So we'll be harvesting cellulose, which can then be used in, I know you've looked at activated, creating a biochar, activating that and using that for microorganic removal. Very much interested in that. We're also looking at using it in construction material as insulation, as a feedstock into the chemical industry. The photocatalytic covers I talked about, that's there. They'll do the lion's share of the work. So they'll stop the nitrous oxide. With a lot of work on sludge optimization. Vacuum stripping of the methane in the secondary digestion tanks, replugging the digesters into series rather than parallel, optimizing thermal hydrolysis to use less natural gas. We've done a lot of work on tackling fugitive methane emissions. So we've been doing a lot of work monitoring with drones and fixed sensors. So get a lot better at finding and fixing leaks. We're building a digital twin. So at the moment, we have a very good mechanistic model of the activated sludge plant, but we're working with Xylem and Siemens, Control AI, Atkins to build a digital twin of the site. That's sort of what it will look like. A bit of a mock-up, but just to give you a sense of the scale of the plant. It serves the city of Stoke-on-Trent, 400,000 population. So a really exciting project. But we don't want to stop there. And I guess my role now is to think about phase 2. And this includes some of the great stuff that you've been working on. You know, you can we're looking at advanced thermal conversion of sludge. Could be cellulose as well, of course. Activating that, using that to remove maybe phosphorus, maybe microorganics, forming organomineral fertilizers, recovering ammonia. There's so many links that, you know, the whole circular economy opportunity is massive. So these are just sort of ideas really at the moment, but this is going to be phase 2. How do we really then go further to make full value and recover, as I say, energy, material and water from our works? So in conclusion, I know I'm preaching to the converted, but it's my absolute conviction that we need to transform how we treat wastewater to be compatible with this low carbon biodiverse future that we need. Thankfully, innovators like your good selves are coming up with loads of potential circular solutions, but we've got to be really good at collaborating to ensure widespread and rapid adoption. Accessing internal funding, be that Interreg or Horizon, great that the UK, I think, are back in the Horizon family. That's really key because, you know, financial challenges at the moment, affordability challenges, big challenges like combined sewer overflows will make it more difficult to get funding for net zero and circular economy. And I would hate for that. There's plenty of other challenges that we need to face into, but we can't forget the need to rapidly decarbonize. And finally, you know, low carbon processes, the resource recovery, we get it right, not only can deliver that sort of net zero carbon that we need, but robust effluent compliance and lower bills. It doesn't have to be more expensive, because as we open up new revenue streams, then, you know, the opportunity, I think, is huge. So I'll leave it at that and take any questions. Thank you.
Thank you, Peter. Now I'm going to say next to you, otherwise they won't see us on the camera.
Yes.
So pretty close. Are there any questions? Because I can't see them, John. No, there are no specific questions. Are there any questions here in the audience for Pete relating to this very nice overview of all the things that are going on at Severn Trent? Yeah, I don't.
Presentation. I was wondering, because you were talking about the UASB reactor.
Yes.
You see if the technology also for the cold climates like we have in Middle Europe?
That's certainly the aspiration, the intention, and it is quite challenging. But yeah, that's what we're trying to do. Take the brilliant learning and work that's being done by Carlos Chinicharo and others in Brazil, and get it to work in
Because you also say which you bring out with the water stream, because it's quite a lot, and I mean we have cold temperatures.
Yeah, absolutely. So you're right.
And I recognize the BOD concentrations are relatively high. So what we could do in between the USB and the nitrogen and phosphorus recovery. So we need an additional carbon reduction step.
Possibly. So
I hope people at home can hear the question. So maybe you should repeat the question before you answer it. Make it a bit more complicated.
no, good point. And if I miss anything, shout out and let me know. So it's, can we get the process, this anaerobic mainstream process, to work in cold, temperate climates like Northern Europe? How do we deal with the challenge at cold temperatures? A lot of the methane is dissolved in the effluent. So how do we deal with that? And do we need an additional step to remove the carbon in the effluent from the UASB? So those three, right? Perfect. So absolutely, the intention is to make it work, and that's why Cranfield have been working on this for sort of 10 years, and at pilot scale, we've shown we can get 90% plus COD removal down as low as 6 degrees. So you can get good performance. You're right that at 10 degrees, for example, over half the methane you generate is dissolved, which is why we have that final methane stripping step, where we're using membrane contactors to try and but it's not straightforward, because you need to apply a vacuum, and that uses energy, or you need to use a sweet gas like nitrogen that then dilutes the methane. So I'm not pretending that we've got it cracked, but you're right, absolutely you need that methane recovery phase. It just won't work either on an energy balance perspective or on a carbon perspective, because that methane will then come out in the river or downstream of where you discharge. So yeah, and then you might be right, we might need an additional. So one idea is you could have potentially an MABR or some other lower energy technology to remove some additional carbon. My hope is that we don't need to do that. We can remove enough carbon, and then we know we'll remove the solids to the UF, and then just deal with the nitrogen and the phosphorus in a chemical absorption phase. But it is work in progress. It's still TRL 5 or 6.
One more question in the back.
Yeah. Yes, thank you very much for the inspiring talk. I had the same question as I would, and my idea was, I love the chart and all the innovations. From the PFA team, I'm kind of missing the bioplastics, and couldn't you put it in that step as well, like using the methane in the effluent and also the rich CND that's in that to feed the biomass and produce bioplastics?
Yeah, and it's a fair challenge. We've not really. So we are. I was talking to you just over. It's about a project that we've just started called biopolymers in the circular economy. So I would say we're a bit. You've done some brilliant work on PHA and bioplastics. We've been watching and learning, but we're a bit earlier on in our journey on that. And the phase 2 that I mentioned, I might not have put it in there. I should have done if I didn't. But that's very much on the radar for getting even more value from the wastewater. But yeah, I guess we see that as our phase 2 at the moment.
Well, I guess I see nice options for cooperation since you're in Horizon again. Then yes. This could be a good opportunity. And I see one more question for Geth, and then we have to move on.
Just one comment. So I think one advantage in the approach will allow us to precipitate phosphorus out of the liquid phase after the carbon peaking step.
Exactly.
At the moment, we are really struggling to get rid of phosphorus out of the sludge edges. And so in your approach, get the liquid, which is rid of ammonia, nitrogen, and phosphorus, we could go for quite different solution.
Yes, exactly right. Thank you.
Okay. Then thanks again, Pete.
Thank you.
For a very inspiring introduction. And then after this nice keynote, I would like to go to the first part of our session on the results of the Vale capitalization project. And the first part is about the removal of micropollutants from wastewater using biochar. And we have 3 speakers on the list. And the first speaker is Hansen from the University of Luxembourg. And he's a professor in urban water management and hydraulic engineering. And well, your presentation probably is already on the screen, the name, so I'll leave the word to you to introduce. Where can we get answer or the arrows? Okay. Well, we can move out of the way.
Okay, thanks a lot for the introduction. Jasper, thanks a lot for the very inspiring talk. Pete, I like it very much, the ideas that you presented. But after all that approaches and strategies, I like to talk with you about toilet paper. So really something else. I don't know what you know about toilet paper in wastewater, in the wastewater stream, and in sewage treatment plants. Perhaps you know that toilet paper is one of the ingredients with the highest amount in the wastewater stream. So each of you, for example, produces or consumes about 85 rolls of toilet paper per year. So when we put the pieces of toilet paper one after the other, it's a distance of 1 kilometer. So it's quite huge. So that means in EU 27, all in all, about 4 million tons of toilet paper are consumed. And perhaps you also know that in wastewater treatment plants, the toilet paper is normally removed in the first stages. So normally in the screen and a little bit also in the grid chamber and the primary sedimentation. And it's defined as a waste, so it's undesirable. It's normally disposed or incinerated a little bit depending on the legal requirements in the country. But on the other hand, toilet paper also consists of cellulose, and cellulose is a very valuable material that could be used for a lot of different purposes. And one of the possibilities to use the cellulose in the toilet paper is the production of biochar. And this was one of the aims in the WOW project. So our idea was to produce biochar, so to valorize the toilet paper and test it for specific applications in the wastewater treatment. The question now is, how can we cover the cellulose? This is not what I like to show you. I'm sorry, there was something going on, but never mind. When you look at the conventional wastewater treatment, then we have the possibility to install a fine screen between the primary sedimentation tank and the grid chamber. And here we have the possibility to recover the cellulose, and the main advantage of installing the fine sieve in between is that after the initial screening and after the grid chamber, most of the particles that would hamper the further process are already removed. So all the large solids, but also the sand. Now let's come to the recovery of cellulose in the sewage treatment plant. Pete already mentioned a Dutch company named Certec, and they developed a specific technology. And in the frame of the WOW project, they installed that specific technology as a demonstration plant at a wastewater treatment plant in Netherlands, in Ede, and operated for a specific time. And that technology is a four-step process. The first process is the cellulose washer. I have to remind you that all the large solids, for example, large screens and everything like that is already removed from the wastewater, but also the sand. So, but what we still have in wastewater is, for example, hairs, fibers, small plastic, and small organic particles. In that first stage of the technology was the cellulose washer. These particles are removed from the wastewater by a mixture of air and water. Second step then is a fine screen. It's a rotating filter mesh for capturing the cellulose. And what we do now is to fed the wastewater on the mesh, and the wastewater drains to the mesh. And finally, we have a layer of cellulose on that mesh. Next step then is a dewatering step. That means that the particles from the sieving are dewatered by a press. And finally, we have a water content of about 50%. And the last and final step is then a drying and pelletizing step, which means that the pressed material is dried in 2 steps with air and flue gas, and then converted into pellets of about 6 millimeters of diameter. Something went wrong here with the presentation. I don't know what, because this is not the picture that I like to show. I'm sorry. But finally, what we have are cellulose pellets with 90% of dry matter. Question is now what to do with the cellulose. What we decided in the WOW project is to use the cellulose as biochar. We have different other possibilities also. I think Peter also mentioned it. So during the process of pyrolyzation, we also have bio-oil that, for example, could be used for heating purposes or for blending fuels. We have a gas that occurs, and the other possibility is also an acetic acid that can be used for improving denitrification on the wastewater treatment plant. But what we did in the WOW project is that we wanted to use the biochar as a supporting material in so-called constructed wetlands as an additional step after the conventional treatment. with the aim of micropollutant elimination. I don't know if everybody of you knows what a constructed wetland is. I'd like to summarize a brief. Constructed wetland is a nature-based system for wastewater treatment. It's used for several purposes in wastewater disposal. And perhaps most of you may know constructed wetland as a decentralized treatment step for small units. So for example, when you have 200, 500 population equivalents, this could be the main treatment step to get rid of the BOD of ammonia, for example, and the phosphorus. But constructed wetlands are also used as an advanced treatment step for stormwater and combined wastewater. And what we know from these constructed wetlands is that they are great in removing micropollutants, BOD, COD, ammonia, and phosphorus. And we know that they have a high capability to remove heavy metals. When we started to work with constructed wetlands, in our literature study, we also saw that there are first approaches for the elimination of micropollutants with constructed wetlands. And we started with the work on constructed wetlands in 2017. So we have experience 6 years, 7 years nearly, and we did a lot of different projects, and we learned a lot in these projects. Especially into Interreg projects that we could carry out. First of all, the EMISIR project, and the other one was the Common Grade project. And to summarize a little bit the lessons that we learned. So first of all, what we learned is that the utilization of biochar in a constructed wetland, which is mainly operated with sand as a soil, could increase their performance, especially for micropollutant elimination. So what we did in the Vale project is to use the biochar that we will produce from the cellulose pellets as an admixture for the soil to increase the ability of the soil to remove micropollutants. And we put it in the soil and mix it in a percentage of 5 to 15. And the second lesson that we learned is that the activation of the biochar, and especially the biological activation by a fermentation, can lead to a further increase of the performance. So the idea of the Vale project was to use biologically activated biochar that is produced from cellulose as a supporting material in constructed wetlands. And these constructed wetlands are used as an additional step for a targeted micropollutant elimination in wastewater treatment plants, especially for small and medium-sized wastewater treatment plants. So coming back to our wastewater treatment plant, what we have on a wastewater treatment plant are these cellulose pellets, 6 millimeter, 90% of dry solids. Now we have to valorize these pellets. Now we have to valorize the cellulose. And in the frame of the Vale project, these cellulose pellets were transported or delivered from the wastewater treatment plant of Ede to a small German company, which is called Klimapharma, for valorization. And Klimapharma has a lot of experience with biochar. And in our discussion, they proposed that based on their experience, they proposed the production of 3 different types of biochar. First of all, biochar made from 100% of cellulose. Secondly, biochar made from 50% of cellulose and 50% of straw. And the next option was 50% of cellulose, 50% of wood. And now we have to valorize the pellets, the cellulose pellets. And this is done in 2 steps. The first step is a carbonization step. On the sheets of peat, we saw, for example, pyrolization. It's the same like carbonization. It's a well-known process for more than 100 years for the production of biocoal, for example. And what Klimapharma is doing, they do carbonization at low temperature, between 600 and 800 degrees. And the reason for that is to reduce the loss of organic material. Because when we carbonize with a very high temperature, then we go more in the direction of biofuel and gas. And we lose a lot of the organic material and we lose the biochar. The residence time in the reactor is between 2 and 6 hours. The next step after carbonization, and this is quite unique, is a biological activation. So normally when you look at activated char, for example, activated coal, this activation is done in a chemical or thermal way with very high temperature. Okay, but here what they do is an anaerobic fermentation on low temperature, 25 to 35 degrees. And the biochar is mixed with additives like minerals, like nutrients, and microorganisms, for example, bacteria and yeast. And that fermentation process takes about 2 to 4 weeks. And this is the final product. We call it Biochar. So we have 3 different types of biochar. So we have the biochar made of cellulose, and we have the 2 types with the mixture with straw and with wood. Okay, the question now was, which kind of biochar should we use? You want the cellulose or the mixtures? Okay, what we decided to make some pre-test in the lab. And when you look at the processes and the mechanism in a constructed wetland, you can see it on the right side. The removal is based on several processes. For example, in a constructed wetland, we have photodegradation by the sunlight. We have photodegradation, so the uptake of pollutants by the plants. But the main processes for micropollutant elimination are the adsorption of the soil material and the biodegradation by the bacteria, which mainly takes place in the first, I would say, 15-20 centimeter of the soil, because here the bacteria and the fungi and the plants are working closely together to remove the pollutants. So what we decided is to make some pre-test in the lab for adsorption capacity, and I'd like to show you some of the results afterwards, and for the biological removal capacity of the material that we used. I'd like to explain in brief what kind of experiments we did in our lab. So we did adsorption tests, first of all, with batch tests on a shaking table. And the idea or the purpose of this investigation was to look for the general removal rates for a dye, indigo carmine, as a proxy for the micropollutants, but also for selected micropollutants. So the aim of the batch test is really to look for the removal rates. So what is possible to eliminate regarding micropollutants and dye? And the second test that we carried out in the lab were continuous tests with a facility which is called rapid small-scale test. This is not a rapid small-scale test. I'm really sorry, I don't know what happened with the presentation. But the idea of that rapid small-scale test is to look for the long-term performance for the removal. So what we can see are so-called breakthrough curves, and I'd like to show you an example afterwards. So what we did, to summarize, we did test this indigo carmine, so with the dye and with selected micropollutants. We did tests with non-activated and activated material, also in different sizes. So we did tests, for example, with very fine material to simulate powder activated carbon, but also with a coarser material to simulate granular activated carbon. And we did tests with the pure cellulose and the mixture of cellulose, straw, cellulose, and wood. And here we can see some results of the pretest. This is also not the picture that I like to show. I'm really sorry for that. But to summarize a little bit, what you can see on that figure below, these are results of the continuous test. Here you can see the batch volumes and the development of the removal rates for the different mixtures that we choose. And to summarize a little bit, what we saw is that the mixture of cellulose with wood had the lowest adsorption capacity for indigo carmine, but also for the micropollutants. The 100% cellulose and the mixture of the cellulose with the straw showed a similar behavior for the adsorption. But what we finally saw is that the mixture of the cellulose with the straw showed the best performance for the combination of adsorption, but also for the biodegradation. So finally, we decided to carry out further tests in another scale, in mesocosm, but also in a pilot scale on a wastewater treatment plant, with that mixture of cellulose and straw and with the activated material. And the results will be presented by my colleague Venditti afterwards. So to summarize a little bit, cellulose is a valuable product that could, but also should be extracted from the wastewater. It's very easy to integrate the technology in the conventional process of wastewater treatment. By carbonization and biological activation, it is possible to produce an activated biochar, and that biochar can be used for different purposes, for example, for micropollutant elimination from the wastewater in constructed wetland, which are really suitable for small and medium-sized wastewater treatment plant as an additional step, where we were really looking for alternatives. So until now, when you have a wastewater treatment plant with 3,000, 5,000 population equivalent, it's not possible to use an oscillation, for example, or activated carbon filtration, because it's too expensive and yeah, really not so easy to operate. And here we have to find solutions and alternatives for that. So from our opinion, this is a perfect example for a circular approach in wastewater treatment. And this was the main idea of the WOW project, to valorize products from the wastewater and give them a value and use them, for example, in the wastewater treatment process. I'd like to thank very much my collaborators in Luxembourg. Sylvia will present afterwards. I'd like to say thank you especially to Irene Salmeron, who did all the experiments. I'm standing here and have the pleasure to present the results, but she was doing all the work. Now she's sitting at home. She would love to have to be here, but she's sitting in front of her computer now and enjoying her first baby. So greetings to her from Dublin. And I'd also like to thank all our partners in the WOW project. It was always a great pleasure to work together with you in that amazing project. Thanks a lot.
Thank you very much, Jo, for an inspiring presentation. And well, already, even without asking, I already see a hand raised, which is very nice. So we already have a question from the audience.
Thank you for your presentation. So when you are mixing cellulose with different ratio of the wood and also straw, why do you think straw is performing better than wood? Is there any structural difference or the human behind inside, or?
Yeah, what we
So the question is if Jo can explain why the combination with straw gave the better results with the elimination.
Yeah, what we, for example, saw is that the surface, the active surface changed. So the active surface was higher when we mixed the cellulose together with other compounds. And the active surface is very important for the absorption capacity. And I think the other thing is that in a constructed wetland, we have to offer the bacteria and the fungi good conditions. And you can imagine that the cellulose is a quite inert material. And when we mix it together with a more living material, that may offer better conditions for the bacteria and the fungi in the constructed wetland. Because what is very important for the removal in a constructed wetland is really the combination of the different processes. It's not only absorption, because otherwise we would have used classical activated char or something like that. Yeah, but we know from our experiments that especially the biochar that is produced, for example, from plants, or in this case, the mixture of the cellulose and the straw, for example, gives ideal conditions for the bacteria. And this is the reason, I think, why.
And also, so what about the mechanical behavior of the mixture? Is it important in your project to see, for example, if you have 100% cellulose, biochar from cellulose, or with the straw, the aggregates or the particles you have, when you have different mixture, you have different behavior, or it doesn't even affect your project too much?
You mean when we change the percentages?
Yeah.
When we change, yeah.
One of them is very very hard. The other one is kind of very powder, and it's difficult for handling,
Yeah.
for mixing.
So we didn't work with different percentages of straw and wood. It's not what we did. So at the beginning we have to decide, because time was running in the project. That was one of the challenges in the project. We have to decide which kind of cellulose mixture of pure cellulose do we take. And at the beginning of the project, we only had the idea to use the pure cellulose. And then in the discussion together with Klimafarmer, they said, okay, let's mix it together with another material. And then we had the idea to mix it with straw and wood. And then we choose for a kind of compromise 50-50. That was the reason. And so we don't know exactly if a mixture 20% cellulose, 80% of straw would perform better. But you will see afterwards that the performance of the material is amazing, I would say. So no need to.
You chose the right the mixture in this case already.
It's so.
Yeah. Okay, thank you. I see we also have a question from the audience saying a nice presentation, and what do the economics look like?
Yeah, we have a presentation on that.
So indeed, the question will be answered later.
Yeah, I think in half an hour, Inka will address how we can deal with that in practice and what is our idea to where to produce and where to use it and what are economic aspects of that.
And I'm very curious because in the beginning you told, well, you produced the biochar from the cellulose. So how many toilet paper do you need to produce how much biochar in the end? Do you know?
It's a good question. And so what we found out and what we were told by the company is that that we have a loss about of 70%. During the process of carbonization and activation. So when I'm not wrong, from 85 rolls of toilet paper, we can produce about 20-30 rolls of biochar activated biochar. So finally, we have about 25 to 30% of final product. Yeah, the rest is a loss during the process.
Then my mind started running. Do we need to go to the toilet more often to be able to remove all the micropollutants or not? But that's maybe another calculation to make. I see there's 2 more questions here in the audience.
Thank you very much for the lecture. It's very interesting. My questions in respect of the soil texture in your column, in these small columns. Were you using artificial soils, the sand, to mimic this constructed wetland? Did you monitor the organisms that were existing in the sand, see what bacteria functioned there from the beginning, or what was added in, or were you inoculating?
Not in that project, but we have one year. Anka was doing these experiments in her PhD thesis, and nowadays we have another project, also a PhD of mine, Fernanda. He's also sitting in front of the screen, and she's doing the same for greywater treatment. And here we will look for the composition of the bacteria at the beginning, and also in the further phase of the experiments. Then we can see what will happen and which kind of experts will develop in the soil.
Yeah. Okay. Thank you. One final question, Pete.
Thank you. Thanks. Really interesting. And yeah, just sort of reflecting on some of the sort of implementation that challenges. And one of the things that's uppermost in lots of, I suppose, reporting minds at the moment and far wider is PFAS. Now, I'm guessing the carbonization process will volatilize PFAS that may be on the cellulose.
Okay.
But do you see any sort of, any benefits or any risks of PFAS, particularly when you apply this biochar to constructed wetland?
The question is about PFAS, and elaborate on that topic. I would summarize it.
Yeah, we were looking for the elimination rate for PFAS. This is something that Sylvia will represent. So we know from further experiments, not with the cellulose-based biochar, but with other biochar, which was made from plants, that we have an elimination of PFAS in the constructed wetlands, but it's not so huge. It was about, I think, 30%. About.
We are also speaking about very low concentration.
Yeah.
The target analysis is not.
It's definitely a challenge for constructed wetlands. You will see it afterwards. So we have a widespread of different compounds that we were looking for. And for most of the compounds, the elimination rate is quite high, but there are specific ones which are very hard to remove. Yes. And PFAS is one of them, definitely.
I guess that's a very nice bridge towards the next presentation.
Yeah.
So thank you very much.
Yeah, okay, you're welcome.
So our next speaker is Sylvia Venditti. She's a fellow researcher also at the University of Luxembourg, and she's a specialist in nature-based solutions for the removal of micropollutants. Yeah, you are. So that's very nice that you're also going to present about that. So moving on from the introduction of you, we now go to the elimination of pollutants using biochar from cellulose. So
thank you.
give the floor to you.
Nice to be again with the WOW family. So we were characterizing the activated biochar that we produce from recovered cellulose. And now we want to go to the next step, which is the application in constructed wetlands for pollutants elimination. So what was our motivation for that? I really like the picture of pit where you see a huge wastewater treatment plant. So this was a bit the base of the WOW project. We were considering how to recover material from large wastewater treatment plants and use this large wastewater treatment plant as factories, right? So what we did in the capitalization call with the use of constructed wetlands was to really make the bridge between a large wastewater treatment plant used as factories and rural areas to solve one of the main issues in the rural areas, which is the pollution of micropollutants. Because we base our motivation on the foundation pillars of the Interreg Northwest Europe program, which is to boost territorial cohesion. So we are not looking only to the large wastewater treatment plant, but to the rural areas and the inclusive growth of rural areas. Because the Northwest Europe zone has huge extension of rural areas, which are characterized from small and medium-sized wastewater treatment plants, which often are discharging in sensitive rivers. Why sensitive small river? Because these rivers, in the dry periods, can be even more subject to the release of pollution, which can have a huge impact in biodiversity. So, especially for rural areas, the mitigation of pollution is essential in order to achieve the good chemical and ecological conditions, which are the main fundament of the Water Frame Directive. So our purpose then was to use the WOW activated biochar produced for cellulose to apply it in a constructed wetland that is a nature-based solution to mitigate the problem of pollution in the rural areas, to make this bridge between the large wastewater treatment plant and the rural areas in the Northwest Europe zone. So why nature-based solution? And why I'm speaking about nature-based solution? I'm reporting here the definition of the Commission. They are innovative approach that have to regenerate areas which are affected from human activities. And how we do that? We want to restore the basic key ecological functions to improve our life. This is a very romantic aim. I'm out of the technology now. And you see in this picture, in the upper part, we have a wetland, which is installed in a rural area. And in the bottom part, we have nature-based solutions that they are fully integrated in urban areas. Everything is around the Northwest Europe. And nobody will believe that these are wastewater technologies because they are fully integrated in the environment. So we were choose constructed wetlands, and we decided to focus to the removal of micropollutants. Why? Micropollutants, we know that they can pose a risk to the aquatic system, even if present at very small concentration. They are pesticides, pharmaceuticals. Probably everybody knows diclofenac, which is the active ingredient of water and pit. You are running, you know.
Yeah, I do know.
Luckily, I still don't use it, but so I think everybody knows what micropollutants are: herbicide, pesticides. We knew that conventional wastewater treatment plants are partially efficient or inefficient to remove micropollutants, simply because they were not designed for this purpose. And we also know that the European Commission made mandatory for all EU member states to monitor 17 compounds. And among them, we have antibiotics, like azithromycin, very known one. So if the micropollutants is a topic globally, for large wastewater treatment plants, it is even more important in small a medium-sized wastewater treatment plant and in rural areas. So it's there that we want to act, and we want to look for the application of our WOW activated biochar. And we know that a solution is needed. So coming again to the constructed wetlands in vertical flow configurations are one of the many nature-based solutions. And we were selecting this one because we know that constructed wetland and vertical flow configuration have aerobic conditions which are favorable to remove persistent compounds like micropollutants. And we also know that there's a kind of ecosystem that is difficult to control because the bacteria, the fungi, they do what they want. But there are a few things that we can choose. One of them is the soil that we want to apply. So maybe we can have an influence in the sorption mechanism. And how we do that, we use in the past and we use admixture. So maybe not everybody remembers, but the University of Luxembourg had a completely different role in the WOW project, in the first phase of the WOW project. There we were producing biodiesel from enriched sludge, where microtrips parvicella, filamentous bacteria are accumulating lipids. So why we are now in the capitalization hall with a topic that is completely different, which is constructed wetland nature-based solution. As Jo said, we are working on this since 2017. Why? Because Luxembourg is belonging to what we call greater region. And the greater region has quite a few issues in terms of micropollutants, because we have a mainly small and medium-sized wastewater treatment plant. If you implement an ozonation reactor as a post-treatment step for the removal of micropollutants, the costs are huge, the energy consumption is huge. So where is possible, it's needed to look for something that has lower footprint and carbon impact. And so we have these two Interreg projects. And again, we want to make a bridge between what we achieved in the rural area, in the greater region, with another program, and what we did in WOW, in the large wastewater treatment plant factory. What I wanted to show is that we had long experience with the different scale of constructed wetlands. We had the laboratory lysimeters. We had 1 cubic meter wetlands where Anka was working, for example. We had the wastewater treatment plant of Echternach, where we had 2 big containers for over 1 year. So we want to apply this experience now to solve the problem to suggest solution in the greater region, but also an application for the WOW biochar. So for this, we use what is called mesocosm design, which is very common in the wetland community. And why is common? You normally use small reactor in the lab that have a maximum a volume of 20-35 liters. And you use them with real wastewater. And this is exactly what we did. Why we were choosing mesocosm? Because a designer like this allowed to conduct many experiments under replicate, control, and repeatable conditions. So what we had, very low cost. What we had is exactly the configuration you see in this picture. We had 2 reactors of 20 liters each, in which we had a basis of gravel that we use as drainage material, and 20 centimeters of soil on top. And we water them in a vertical flow configuration. A vertical flow constructed wetlands is water from top to the bottom. It's not water in continuous, but in different cycle of water. Why? Because between one cycle of watering and the other, we want to allow the water to percolate along the soil. So from top to the bottom. And this also allowed very good exchange of oxygen, because it's an aerobic system. The 2 mesocosms were planted with the same plants, microphytes, which we were using in Emissure and coming grade, which are Phragmites and iris. Phragmites has very long root. Normally, it should allow also a better transmission of oxygen along the depth of the soil. And iris has short root. We know from the PhD of Anka that the area around the root of the plants is probably one of the most active for biological degradation. And this is also why everything is happening maybe in the first 15 centimeters of depth of the soil. So the first step was to decide what are we measuring. And we defined a first list of compounds, 28 compounds, to measure with LCMS, so with the mass spectrometry target analysis. We have 16 pharmaceuticals, diclofenac, ibuprofen. Everybody was using ibuprofen once, I think. We have a set of antibiotics, beta blocker, hormones, but we also have one of the fluorosurfactant, PFOS, that most known in our previous monitoring. And we have quite a few herbicides that have been banned some years ago, like Tyrone, but they are still present in the surface water. And we also have, like, for example, caffeine and sucralose, which can be considered like a tracer of the human activity. So we have a representative list of 28 compounds. And for these two reactors, we decide to collect wastewater, a real wastewater effluent, from a wastewater treatment plant in Luxembourg. You see in this picture how the wastewater sanitation is managed in Luxembourg. We have syndicates that are treating the water in area of Luxembourg, and we were selecting the syndicate of Citero, which is the orange one, and we were collecting the water for our experiments from the wastewater treatment plant of Beringen in Mersch, which served 70,000 people equivalent. Why we did that? The effluent has a good quality. It was close to the University of Luxembourg, and is quite representative for medium-sized wastewater treatment plant. Even if in a country like Luxembourg, it's quite a big wastewater treatment plant. What is important when we are facing micropollutant elimination and when we assess a catchment is that not all the compounds that we were selecting are relevant. So we measure them in the influent and the effluent of the wastewater treatment plant. And what was important for us, because we use the effluent of the wastewater treatment plant as influent to our mesocosm, is that only 12 compounds of our list are really relevant. And for example, I could not measure any removal rate for PFOS because the concentration were far too low. So for me, it was really not even reasonable to do that. We did two types of tests. We were we were watering the two mesocosmos in a batch mode. We were watering there every 3 days for a period, and then in continuous, every day, intermittently, with 2 cycles of water. Why we did that? We wanted to get close to some wastewater treatment plant that already have a constructed wetland in place, and I will tell you later. And we also want to have the same hydraulic load per irrigated surface that we had in the previous project. In the previous project, we were using 100 liters of wastewater irrigated per square meter of surface of constructed wetland per day. But we had a depth of soil of 45 to 90 centimeters, and now we are talking about 20 centimeters. So we were also refilling only to the volume of the soil. So just to give you an impression why we were watering every 3 days, and the mesocosmos were getting water only the first day, then they were draining, and the third day, they had no water at all. They were just resting. This is because there is a wastewater treatment plant in Germany that is called Rheinbach, where you have a 3 segment. This wastewater treatment plant has constructed wetlands as post-treatment step, where you have 3 segments, and every segment is water every 3 days. So we really wanted to see if we can get a better removal, just reproducing the conditions that are also already like in one of the wastewater treatment plants. And the results were really promising. I will give you just an example of diclofenac. We had the full removal of micropollutants already with the first flush, because we have 2 flushes per day. And the abatement of the concentration of micropollutants you see is almost close to 100% already after 4 hours from the flush and after 25 hours. And the other important information that you see, that there is no difference in performance between the soil use with activated biochar and the soil use with the activated biochar that we had in the previous project MSU. So the WOW biochar produced from cellulose seems to have the same performance of the biochar that we were using in the previous project. Here you see the 12 compounds. The general elimination is about 90% for the biochar produced from cellulose, which is slightly lower than the 94% of the biochar that we were using in the previous project. So really, the activated biochar from cellulose show very, very high performance. What is also important that for a compound that is the flame retardant TCPP, where we show already in previous project that the elimination was quite low, we really have a consistent results. So still lower elimination. Finally, we saw that if we operated the mesocosmos in continuous, we water them every day, 2 times a day, we have similar results. Here you see the average removal over 5 months of operation is very, very high, except for the TCPP, which is the flame retardant. We are above 89% for the activated biochar from cellulose for 12 compounds, very, very high, and very similar to the biochar that we use in the previous project. But what is more important is how we translate these results into policy. In 2020, Luxembourg was releasing the first guideline for micropollutant removal. 13 wastewater treatment plants in Luxembourg were considered eligible to get funding for a post-treatment step with any kind of technologies. And the legal requirement was to comply with the 80% elimination for 4 mandatory compounds, which are diclofenac, carbamazepine, clarithromycin, and benzotriazole. Carbamazepine is an antiepileptic. So what I showed here is the global elimination that you have calculated from the influence of the wastewater treatment plant to the effluent discharge in the river. And you can see I calculated the removal, total, partial, not removal of the contribution of the wastewater treatment plant, which is the black bar, and the contribution of the post-treatment step, which is the constructed wetlands, with the mixture from MSU, the activated biochar from the previous project, and right, the activated biochar from cellulose. In red, I want to highlight the removal for the 4 mandatory compounds. And you see that for all of them, the contribution of the wastewater treatment plant is very low. You absolutely not reach the 80%, and it's possible to reach the 80% only with the post-treatment step. And with the constructed wetlands, with our admixture, we are able to fulfill the requirements and go far beyond, because we have a very high global removal rate. And the second important thing is these results left are from our previous activated biochar use from the Emisure and the Coming Rate project, consistent with the past data that we have from all the previous tests that we did, very consistent. And right, you have the performance when you use our WOW activated biochar. And the differences are minimum, very, very little. So definitely the activated biochar from cellulose perform well. So in conclusion, what we realized with this test using real wastewater is that the WOW activated biochar from cellulose is definitely suitable to be used as a mixture when it's mixed with sand. The sand that we use is a bentonic sand in a constructed wetlands for the removal of micropollutants when the constructed wetlands is used as a post-treatment step. That the performance of the activated biochar from cellulose are really similar to the activated biochar that we used in the past. So results are really consistent. And that the effort to implement this solution or this admixture for a small catchment will then in Zealand will then be presented from India.
Thank you very much, Sylvia. For a very nice overview. I already see there's a question in the back of the room.
Thank you for the presentation. What minerals put into the what do you treat biochar with?
Sorry?
What do you treat biochar with before you commence the absorption? So you convert cellulose into biochar. What activation do you do with?
This was a biological activation, and as Joachim was saying, the biochar is activated by fermentation, so the yeast and bacteria are inoculated for a period of time, like between 2 and 4 weeks, 6 weeks. The fermentation is controlled with the pH and the temperature, and in theory, one should realize when the fermentation is finished to then use this activated biochar mixed with sand in the constructed wetland. But it's very different from chemical and thermical activation because actually you don't really increase the surface capacity. It's more that this biochar is then supporting the biological growth in the ecosystem of the wetland.
Okay, question here.
Thank you very much for the lecture. But I think my question is more related to the previous section. My question is that, based on your experience, do you have any idea if, for example, cellulose, if we play with the size of the cellulose partner, when the nanocellulose give us a biochar with another performance, do you have any idea about this?
The
No.
question about the effect of playing with the cellulose and the
No,
particle
we were
size.
not doing that.
No.
We were just we did just this test mixing 50% cellulose and 50% straw or wood waste. We didn't play with other properties.
Yeah. One final question here in front.
Yeah, just a really good lecture. Thank you very much. I just question you're talking about rural communities and the practicalities of the system, and you were using secondary treated effluent.
Yeah.
My question is, in a lot of rural communities in Ireland, people are usually using a septic tank and soil treatment.
Yeah.
And so the big challenge financially is a lot of people don't want to pay extra for, additional treatment. You're getting, 40% of our population, about 30 to 40 use on-site systems. So making them pay for a 2,000, 3,000 euro second treatment system. So my question, I guess, is if you get people clustering together for a connected system, could this work as a secondary treatment system?
I mean, it's known in the wetland community since years, but it's a completely different application because as a secondary system, you have a much higher organic load suspended solid, while here we were actually treating a water effluent with very high quality.
I guess it's more in respect of the micropollutants as
Yes.
well. If the idea of are we seeing more micropollutants coming in
Yes.
from the primary, and if you have to save money, are we increasing the loads onto these systems as well?
Yeah, and it's really a completely different application. For example, in this case, as post-treatment step, you hardly will have a flocking.
Yeah.
As a secondary step, we probably have to exchange the first layer very frequently, and for post-treatment, it might stay like 30 years without being.
In respect of clogging, you know, there is something to be said that it's not necessarily always a damaging effect on the system, because
Yes.
you know, it's an over assumption that because you're seeing clogging, but in reality that is a microbial ecosystem in there as well.
Yes.
So there could be a benefit from that, because we're talking about organics here as well.
But it's true, but we use a more fine material compared to a veteran that you will use as a secondary step. There is much more gravel, expanded clay that are you need to have a much coarse material because it's also a filtration system of solids, suspended solid or material, bigger particles.
Maybe a nice topic for the coffee
Yeah.
break later on. But before, thank you very much, Sylvia. Before we go to the coffee break, we're running a bit 10 minutes late, but we also started a bit later with this session. But we will have a coffee break, but not before we will have Inka Hobus presenting here from the Wupperverbands, where she's a project engineer, and it was already mentioned a few times before, also with the questions, and what about economics? And well, you're going to shed a light on that. So.
So yes, I want to show a small case study for a catchment area in Germany. The agenda is that I will show the boundary conditions for the case study, the solution already you and Sylvia shows, but how it will look for this case study, the design for the pine sieve and the constructed wetlands to use the Vale biochar, and at the end I will show the result. So here you see a picture from the catchment area. It's a river Blies. It's a border from France to Germany, a small river, and the catchment area you see is only for the German part. It's a very rural area, and you see all those small yellow spots. These are the wastewater treatment plants, and there are a huge number of very small treatment plants with a capacity from only 5,000 population equivalents. The treatment plants discharge their wastewater the most time in small water courses, and sometimes directly in the near of the close to the source. In the first project, we look at the balance for the pollutant dichlorphenac, to show in this small part of the river Oster, and in the diagram you see the dichlorphenac concentration along the flow distance of the river. The river has only a length from 30 kilometers, and at the top you see all the wastewater treatment plants which discharge their wastewater into the river. And you see at the when the first wastewater treatment plant, Hobus Vale, discharge their water, the dichlorphenac concentration is directly above the quality criteria which are discussed from the European Union for the environmental quality criteria. So here you see that we need possibilities for small wastewater treatment plants to improve the effluent, and the requirements are, of course, that we know that we have to use technically simple, and the other point, a system which is with low operational effort. And I think the constructed wetlands fulfill both points, so that you can install them and you only have to check often to see, or sometimes if it works, but there's not a lot of work and to do to keep them working. So we decided, we did different scenarios, but I only want to show one scenario where we install 3 fine sieves, or 2 to 3 fine sieves. It depends on the aim you have, to recover the cellulose at bigger wastewater treatment plants. These are the orange cycles. There we use the cellulose in order to produce directly the raw biochar for the constructed wetlands in the same catchment area. And the green circles are, there we will implement the constructed wetlands with biochar. And these are at small wastewater treatment plants smaller than 5,000 inhabitants. So what is the aim where we want to install the fine sieves? It's at a location where there's no primary clarifier and also where there's no digestion. Because if we implement the fine sieve, we take the primary sludge a little bit outside, and so we have not any more sludge for the primary digester. So the 3 locations at the bigger wastewater treatment plants we choose is there were no clarifier and primary clarifier, no digester. So we can use there, take out the cellulose as a resource for the biochar production for the constructed wetlands. For the calculation, we decided, we have no measurements, that the specific cellulose load is 32 grams per population equivalent a day. And yes, there is an additional advantage for the wastewater treatment plant where we want to install it. There's one wastewater treatment plant where they want to enlarge the capacity at this wastewater treatment plant. And so with the installation of the fine sieve, we reduce the load to the main treatment of the treatment plant, and we reduce the oxygen demand, or we can put additional enhance the treatment capacity. So for the design of the constructed wetland, here you see one wastewater treatment plant. In this figure, it's the wastewater treatment plant Hobus Vale. It's about 3,000 population equivalents. And as Sylvia told, there are 2 different design for the constructed wetland. It's a surface load that it should be around 0.2 cubic meter per square meter a day. And this wastewater treatment plant has a lot of filtration water. So so we need there 7,800 square meters. Sorry, it's not cubic meter. So you see it's quite big. So at the first step for this wastewater treatment plant, we would suggest that they have to reduce the surface as an infiltration water, because here you see the normal design when you have not a lot of infiltration water or water from the sewage from the rainwater, that you only need 0.4 square meter per population equivalent. And so this would be 1,200 square meter. And you see it's always the same size like the wastewater treatment plant, which you see here. It's a actuated sludge system. It is the most time near the wastewater treatment plant is placed to install this system. And for the design of the constructed wetland, we also calculate the amount of biochar we need here. So it's 180,000 kilogram of biochar we have to produce from the pine seeds in the same area. And so here you see the first results of the case study. Here you see again the dichlorphenac concentration in the catchment area, and the gray line was the current conditions, where you see that at the first discharge of the wastewater treatment plant, Hobus Vale, you have an increase of diclofenac to 60 nanogram per liter. And due to the constructed wetland, where we decided that 80%, so less than the 90% or 100%, which we hear in the presentation before, can be reduced with the constructed wetlands. And the blue one was when we install at 3 wastewater treatment plants the constructed wetlands. So we are the most time above the quality criteria for diclofenac. And if we want to be below for all variants, we had to install it at each wastewater treatment plant. So the question is, of course, as the economic, how high are the costs? So it depends on the infiltration water, or how much water comes from the rain. If it's very high, then you need higher costs. So we are still now in the calculation phase, and in the end report, the data will be inside for the implementation from the both systems, the constructed wetlands and also the fine sieves. So as a conclusion, the combination of cellulose recovery with fine sieves in order to provide the raw biochar and the micropollutant removal is in one river catchment area possible. Although the load reduction from the small wastewater treatment plants is, in comparison to the whole load from all wastewater treatment plants in the catchment area, very small, we also calculate this is the impact on the river quality very high, because we have these very small rivers, and so it is really necessary to look at the case as it's a catchment area where you have to put technical installation to improve the removal of pollutants. And for us, for the so we didn't show today the economics, because we have to discuss or to do further investigation about the hydraulic load when you have very high water flow income, like we have it here at this river catchment area. The investment costs are really high, so you have we have to cross-check the data. So yes, thank you.
Very much, Inka, for this first insight into economics. But as you already said, in I think about a month, the report will be available on the WOW website. So please do visit the website. Are there any questions for Inka? Were there any questions online?
No, those are all questions.
Okay. Then I guess also considering time, thank you for the presentation. And as I said, we are running a bit behind. So I would like to say we will reconvene at, and then I have to think, because we have 2 times, 11:40 here in Ireland or in the UK, and for 12:40, so you can have a quick sandwich in Europe. And then we hope to see you back, because in the second part we will talk about producing PHA bioplastic from residual streams. So see you in about 25 minutes.
Hello, everyone online. We're just preparing here, so we'll start back in 1 minute. So we'll start back in 1 minute. Thanks for your patience.
So welcome back, everyone. I hope you had a nice break. We did here with coffee and cookies, so that's always nice. So now we go to the second part of this final event from the Water Capitalization Project, which is about the production of bioplastic PHA from residual streams, which I already mentioned a few times before. So in total, we have 5 speakers. And the first speaker should have been my colleague, Alexander, but he turned ill, unfortunately. And Alexander, if you're home, I hope you get well soon. So for me, the big task to try and talk you through the presentation that he made, because we think it's essential to tell the story about PHA, from where we were and so to where we are now. Then I also have to watch my own time, so I'm going to start my timer and see if I can stay within the amount of time. So this presentation that I will talk to you about is the selection of locations for PHA production. And well, we always start the first slide with the goal of the study that we did. And in this case, we wanted to use GIS, so Geographical Information System, to define the most feasible locations for PHA production facility. Because what we found out is we discovered in the first WOW project that there are many sewage treatment plants in Europe, but not all are suitable to have a PHA production facility. And also, do you need at each sewage treatment plant a production facility? So that's why we did this exercise, and we were considering two main parameters, which were capacity and transport. And the scope of this presentation will be on Scotland, but I'll show you later on. We also did the exercise for other regions in Europe. And then the first question is always, why do you use GIS? Because you'd logically, if you say at where would you build your PHA facility, then you would say, yeah, choose the biggest sewage treatment plant, and then you would be safe. But we always think you have to first decide on the amount of possible facilities. So how many facilities do you want? Do you need? Do you need multiple large size facilities? And also you have to look at the average size wastewater treatment plants in between multiple larger ones. So how you deal with this aspect. And then you see that there's always an equilibrium that you have to take into account between the size of the sewage treatment plant, the distance that you want to travel, because distance is money. It's not very sustainable to go transporting a lot of sludge from one location to the other. And also, what's the optimum capacity that you want for a PHA production facility? So when you look at the possibilities to set, what we did is we look at maximum distance, we look at maximum facilities, and also the ideal amount of the total capacity that you want for a sewage treatment or for a PHA production facility. Well, and then the nice thing with GIS, you can, it's a software, you can calculate as much as you want. You can also get lost in that, I know from experience, but it's a good tool to do the selection. So when we look at defining the selection methods, what we did is we got data from the Urban Wastewater Treatment Directive. So we have the wastewater treatment locations in Scotland, and we also have the different technical specifications. And what we set out as one of the requirements was that we needed 2 million people equivalents for a feasible PHA production plants, because then you produce about 5,000 tons of PHA per year. And that's the outcome that we had from the previous WOW project, the first WOW project. So that's one of the starting points. And what we did, we considered all wastewater treatment plants with a primary treatment, because you use the sludge from the primary treatments for your PHA production. And we only looked at the wastewater treatment plants with the capacity of bigger than 50,000 PE. And then to make it even a bit more complicated, I would say, because what you can do is you can transport wet primary sludge, but then you're transporting a lot of water since it's only about 5% dry matter. So what you could also do is you could have a dryer installation on a location, and then you dry the primary sludge first, and then you transport it, and then it makes out that you obviously have less transport. And in this case, the cutoff criterion is that wastewater treatment plants bigger than 3,000 people equivalents can have a drier location on site. Well, then let's go to some pictures and to make it a bit more visible. So if you look at the potential for Scotland, here you see an overview of the different sewage treatment plants in Scotland. And the bigger the circle, the bigger the amount of people equivalents you have for the sewage treatment plants. So to give a few numbers, so we have about more than 150 sewage treatment plants bigger than 2,000 people equivalents. when you look at, in total, there's 6.1 million people equivalent in Scotland. So that would mean if you go back to the 2 million that you need for a facility, you would have a maximum of 3 facilities in the whole of Scotland. That's the simple calculation. Well, I also told you about bigger than 50,000 PE. So that's about 27 wastewater treatment plants. But if you only consider those, so not only the bigger than 2,000, but only the bigger than 50,000, then you already lose 1.5 million people equivalent. So you're only left with 4.6 people equivalent. So that would mean, if you keep that criteria, that you only have 2 facilities in the whole of Scotland, to give an idea. Well, shouldn't be a surprise if you know a bit about Scotland, that we have 3 cities that, or in this case 4 wastewater treatment plants in 3 cities that have the biggest capacity. So we have the one in Aberdeen on the east coast, we have the one on Edinburgh, also on the east coast, but then a bit more southwards, and we have 2 in Glasgow on the west coast of Scotland. Well, then if we look at those 3 different locations, then what we see for Aberdeen, we striped that off, or said, no, that's not a good location, because if you look at Aberdeen, the people equivalent accounts not over 900,000 PE within 160 kilometers. So that's the reason why that fell up as an option. Also, the same counted for Edinburgh, because it didn't come over 1.5 million people equivalents before you had an overlap with Glasgow. So then you have a transport issue. Where do you put your location? So the most feasible one in this case for Scotland was Glasgow, with 2.6 million people equivalent within 45 kilometers. So quite a short distance to travel. Well, then we can go to different scenarios, and that's also something that Inka later on with the economics will come back to, and I think also Pete will touch it a bit with the sustainability parts, circularity parts. Well, you look at the chosen facility, so it's a shield hall, sewage treatment plant facility. And then when you look at the amount of facilities within the 45 kilometers distance, you see that there are 12 sewage treatment plants within this distance, with the total amount of 2.6 million people equivalent, as I told you in one of the previous slides. So here you see the amount of travel that would be needed. And this location was chosen because of the shortest travel distance when you look at the scattering of the different facilities. Well, they are listed over here. So here you see the 12 contributing facilities within the 45 kilometers distance of traveling. So in this case, that would be when you look at the scenario of 2 million people equivalents transporting primary sludge. Again, with the chosen facility, so the shield hall sewage treatment plants, you can stripe off the smaller ones, because you want an optimum of 2 million people equivalents. So we lose 600,000 people equivalents because that's the optimum scenario of the PSA producing facility. And then when you go towards the 2 million people equivalent, you see that the travel distance is shortened to 20 kilometers instead of the 45. Then the overall picture of this scenario, so 2 million people equivalent transporting primary sludge, so a lot of water. In this case, with the 7 facilities, you come to a total transport amount of 180,000 kilometers per year that you would be traveling your primary sludge to the central location. Obviously, that has an effect on economics and on circularity. And as I said, that will come back later with the other presentations. You also have the other option, as I told you. What you could also do is you could dry the sludge on the facility before you start transporting it. So you have less to transport, but then obviously you have to build a dryer location at different treatment plants that has an economic effect again. So that's the other scenario that we looked into. So in this case, we only transport dried sludge of facilities bigger than 3,000 people equivalent. And then you come to 4 contributing facilities within a 42-kilometer distance. So here you see the ones that drop off because they are smaller than 300,000 people equivalents. So that's what you end up with. And then you see that, well, the chosen facility is still the same. You have 4 sewage treatment plants which contribute, which all have their own drying facility. There you still have 2 million people equivalent that you need to for the minimum PHA facility. And then you also see that the amount of kilometers that you have to travel drop a lot, because you come from 180,000 to only 16,000 kilometers that you have to travel your sludge. Well, and these 2 scenarios, those are the ones that we used also for the economic analysis. So this gives you a bit of an idea what you could have for Scotland. And we also did the same analysis for Ireland, and we also did one for the Saarland region in Germany as well. So those were the different scopes that we had. And if you're interested in the outcome and also a much more elaborate explanation about the whole GIS exercise that we did, you can find the reports on the WOW website. I think in a couple of weeks they should be there. And the further steps, so this was the starting point for us. So the further steps were financial analysis of the different scenarios, as I already told you, and also the circularity analysis that we did using these scenarios, and both of them will be presented later on during this session. And then I'm already at my last slide, and well within time, I see, so that's nice. Well, it's already said a couple of times before, so these are the partners we work with, and we couldn't have done this without, so that's very nice to mention. And then, yeah, I can only say, are there any questions which I may be able to answer?
So perhaps I will ask the audience if there's any questions to allow Jappe a moment. Please.
I don't know.
Maybe one question, because you mentioned we had Scotland, Ireland, and Saarland that are all very rural, more or less rural countries or areas. So can we say it's kind of a worst case scenario which is investigated, and there will be better options if you go to the more dense urban areas than the populated urban areas?
Repeat the question indeed, but you remind me of John. So the question was, so the regions that we looked at are very rural regions. Would it be a worst case scenario? I would say yes. Because also you have regions, well, in the Netherlands, but also in the western part of Germany. We didn't choose the region with the most urbanized region in Germany, but where you have very big cities, then of course you could already have a PHA facility in one specific city, and then still you would look, are there any sewage treatment plants in the surrounding areas that you could also use for your production? But I would have to agree that this is a worst case scenario. Yeah.
And in respect of traffic congestion, you know, often sites are very far away from urban centres, but in respect of like looking at Glasgow, somewhere right in the heart of it, you know, if you the fuel costs and the increases on that, you know, is that something to consider when we're selecting sites, or even to have locations that are a bit outside the urban space as well to prevent, you know, if look at the logistics of that.
Yeah, a good question. I would not choose a location which is in the center of Glasgow, and also not in Dublin, by the way. We came by bus from the airport, and well, I don't want to see a few thousand trucks going to the city center. Fortunately, often you see sewage treatment plants are a bit more on the outer region of the city. But indeed, that's something to take into account. We didn't do that. We only looked at we looked at actual transport routes, but we did not look if it's a route with a lot of traffic congestion, yes or no. That would be a nice addition, by the way, to look into. Yeah. Okay, then can take myself. We go to the next presentation. Because, well, I talked a bit about location for a PHA production facility, but of course you also all want to know about the production of PHA itself from residual streams. So that's why our next speaker is Cora Lauwmeijer from the University of Kaiserslautern, and she will tell more about the PHA production process.
Thank you very much, Jappe. Thank you all for joining here in person and also for everybody joining online. So right now we heard a lot about PHA production from primary sludge, like talking about municipal carbon that we can recover. And now we will get into more of the focus of the capitalization part when it comes to PHA production. And we will look at the production of PHA from residual streams. And in this case, in residual streams from the food industry. Oh, okay. So the agenda of today, I will give a quick introduction again into the WOW project, which everybody by now knows about. And I will talk about biopolymers. So in this case, polyhydroxyalkanoates, so short PHA, give an impression of our beautiful pilot plant setup that you can see in the picture over there, and give first results or give the results of the PHA production from residual streams of the food industry and finish with an outlook. So first, I think we can all agree wastewater is not a waste, but it's a resource, and we want to elaborate on this idea more. And in this WOW project, as we heard in the morning sessions, the former project focused not only on PHA and biochar that we heard about today, but also on different residual streams or streams that we can recover. And the production of PHA from primary sludge has been shown that it's possible. So Thomas Uhrig, my former colleague, he worked on this and did an amazing job showing that the production of PHA is possible, and the results you can find on the project homepage already. So now, what are PHA? So PHA are a group of biodegradable polymers, and they act as a storage molecule for bacteria. So when we eat a lot, we accumulate fat, and in bacteria, what they do is they accumulate polymers. At least some of them do. And those PHA producing bacteria are present in waste activated sludge or in the excess sludge that we have in our wastewater treatment facilities. And by using a process or enriching the amount of bacteria that are able to do this, we have the possibility to produce PHA using the bacteria that are already there and then accumulating PHA within their cells. To do that, we need a certain feedstock, and this feedstock is full of volatile fatty acids, in short VFA. So it's organic acids that we can achieve or that we can produce by the fermentation of residual streams. So as mentioned before, for example, primary sludge, or also residual streams from the food industry, and use this as a substrate for the enrichment and the PHA accumulation within the bacteria. It is known that the VFAs, so it's a group of different organic acids, and it is known that VFAs that have an even number of carbon atoms end up to be converted to PHB, while the ones with uneven amounts of carbon atoms are transformed to PHV. So basically, keeping this in mind, the feedstock already gives you an impression of the PHA that will probably be produced by the bacteria. As you can see, the production chain is a rather long one. I will try and guide you through it from the top left up to the bottom. So we start with the acidification process, which is the first stage. And here we put the residual stream into anaerobic conditions, producing the VFA-rich fermentation liquid that we can then use as a feedstock in our later process. To do this, we do a separation of the solid and the liquid phase to reduce the amount of dry matter and have a VFA-rich stream that we can easily use for the PHA production. Here we start in the second step with the enrichment. So taking, as I said, the excess sludge from a municipal sewage treatment plant, or as we did in the capitalization process, we took it from an industrial site. They also have often industrial sewage treatment plants, and used the excess sludge as an inoculum. So basically as a first starting culture. And then from there on, we develop it. So we have a certain feeding regime. It's called feast and famine. So one time they get a lot of organic acids, feed on this, and then they have a selective advantage above the bacteria that they cannot accumulate it. And therefore we enrich the amount of bacteria that are able to produce PHA. And with this culture, we can then go into the next step and perform an accumulation. So basically what we use there is the well-known yo-yo effect. After dieting, everybody knows it. We like to feed on and stack and accumulate. And this is especially as well what happens in the bacteria. So they have like a luxury uptake, it's also called. And from the accumulation, we go into the downstream process. Or this is what is considered as the downstreaming. So now we have the bacteria that is rich in PHA, but we have to get it out of the process. And we heard about the dry matter content before. So we don't want this huge amount of water. We want the bacteria with the PHA in it. So we need to have a dewatering step and a drying step. And from there on, we go to the extraction step that was performed by our partners at Avance. Big thank you on that side for working with that. And from the extraction, when we have the PHA extracted from the dried biomass, we still need to do the polymer processing, because we end up having a polymer, but you can't just use it and do products. You first need to find out about the properties. You need to add additives, do compounding, and this was done by our colleagues at the Lab University of Applied Science in Finland. So thanks for that, and we'll hear about that in the next presentation. I'm looking forward to it. So the substrate from PHA production, I mentioned it briefly before. So we have an anaerobic fermentation. In this case, a lot in Germany, at least a lot of big sewage treatment plants have anaerobic digestion already in place. But we don't want the full process to happen. So as we can see here, it's a process that contains of 4 different steps, but we don't want the production of methane in the end, which is favored in the anaerobic digestion to produce biogas that you can then use for energy production. What we want to end up with is the VFAs. So we need to prevent the shift from the VFAs to the biogas. And we do this suppression of the bacteria by keeping the pH below 6 and also by keeping the sludge age below 8 days. So the process of PHA production at pilot scale was operated for quite some months with 2 different residual streams of the food industry. I will come to that in the next slides. And in total, I did 20 weekly acidification batches where I didn't use pH control at 34 to 36 degrees centigrade, keeping it nice for the mesophilic bacteria. And I also did 3 enrichment cycles of 2 to 4 weeks per residual stream, with 2 to 3 accumulations per week without pH control. So this is what the process you saw before looked like in the pilot plant. So just as a quick snap. And as mentioned before, all the details will be in the report on the homepage. The objectives of the pilot plant operation was to investigate different residual streams of the food industry for the PHA production and pilot scale. And before we went to pilot scale, we did screening experiments. So we did those together with our partners at Avance, in totally researching for 7 different residual streams that we can use. And here it showed that brewery substrate, like the effluent from a brewery, is very feasible. So we started with that one. And the next residual stream that we used was from a fruit juice company. We also wanted to characterize the VFA-rich substrate and see differences from the different residual streams, investigate the influence of the substrate composition on the PHA production process, because as we know, there will probably be one, and to characterize the produced PHA. So coming to the residual streams, the properties of the first residual stream that we used was from a brewery, and this brewery is operating all year. So the whole year they are producing this residual stream that they have, and they also have an on-site treatment and a buffer tank. And as everybody knows, when you have a buffer tank, you at least get kind of the peaks usually out of the system. And the composition of the residual stream was rather stable throughout the experiments. In the graph, you can see the concentration of the chemical oxygen demand, so the COD of the filtered sample, and also calculated to the amount of VFA within this COD, represented by this orange bars. And you can see here that the amount of the VFA of the total or of the soluble COD was quite high. And on the second y-axis, you see the concentration of nutrients, in this case of orthophosphate and also ammonia nitrogen, because bacteria don't only need carbon to thrive on, they also need some nutrients to work properly. And the produced substrate that we achieved, we saw that the carbon to nitrogen to phosphorus ratio, which is usually aimed for to be 100 to 5 to 1, was quite suitable with the produced substrate, because here we had C to N to P ratio of 100 to 2 to 0.8. And also, as I said before, we had around 70% of the soluble COD that was represented by the VFAs. One remark I want to do here is the substrate number 6, because you see there's a high peak and you might be wondering why that was. There was some issues at the facility which led to some beer going down the drain. So basically this is what happens when you use beer for producing the residual or producing the feedstock for PHA. So we had very high amounts of the VFA concentration on that day. Now when I change to the next slide, have a look at the concentration scale of the COD, because it will go up now by 10,000. Now we're talking about the fruit juice. So the fruit juice, you see, it has very different properties. So first, it's a campaign. So apples are not growing all year round. Unfortunately, we have them in autumn. So right now they are producing, but bottling the fruit juice is happening all year round. So this means there is a difference in the residual streams that we have during the fruit juice campaigns and also during the bottling. So this means also that the availability changes during the year. And this juice factory does not have on-site treatment, but is connected to a municipal sewage treatment plant. So also no buffer tank. The produced substrate here look very different. And if you keep in mind the favored C to N to P ratio, you will see that here we might have a problem, because looking at all the dots lining up around 0 for the concentration of the nutrients, we experienced that we had problems with that. Like there was not enough nutrients for the bacteria to grow on. And during the experiments, we also realized that we need to add nutrients. Otherwise, this is not a feasible feedstock for the production of PHA. Also, what we can see in comparison to the brewery substrate is that the amount of the VFAs from the COD is a lot lower. So here we're talking about, on average, 37% compared to the 70% that we had before with the brewery. So already here we can see it's a very different feedstock. Now looking at the VFA composition of the different substrates, I also included the substrates of the primary sludge that Thomas produced during his time with the pilot plant operation. I'm not going into detail with the color. Just be aware each color represents a different VFA. And you can see while for the primary sludge, the concentration or the different color blocks, let's say it like this. So the different VFAs are quite stable throughout the year. It's kind of the same for the brewery residual stream, but the fruit juice company's residual stream looks completely different. So here we see there's high fluctuations and also changes, like for example, the substrate 5 and 6, there were high amount of caproic acids, so longer change VFAs as well. And this also showed in the PHA accumulation results. To conclude, we can see here that different residual streams result in different substrates or a different VFA composition within the substrates. And also that not only there is a difference between the substrate of the different residual streams, but also of different batches. So you can't say one residual stream has always the same composition after the acidification. The primary sludge, as already said, yields a quite stable VFA composition throughout the year. And the residual stream of the fruit juice company, as we saw before, resulted in a higher amount of VFA, so higher VFA concentrations, but also a lower ratio of the VFAs in comparison to the soluble COD. Now looking at the PHA composition that we achieved using those different substrates, here I will talk about the HB, so the monomeric composition. So the hydroxybutyrate and hydroxyvalerate, which was measured by gas chromatography. And here we can see that for the primary sludge, we see mainly in all of the cases, the yellow part, so HV that was produced, while we see for the industrial residual streams that were high in sugar, we produced mainly HB. So that's also interesting if we keep in mind that we want to maybe adjust the different properties of the polymer that is produced. So the PHA that was produced from fruit juice also did not only achieve PHB and PHV, but also HH, so hydroxyhexanoates, which opens a whole new possibilities that we want to explore in future projects. And also the future objective will be to adjust the composition, because now we showed that it's possible to produce PHA, but now we also want to try and turn the different screws to make it suitable for application. Now coming to the take-home messages and the outlook. As I said before, the municipal sewage treatment plant, we have stable VFA and PHA compositions throughout the year, also during the winter. And there also aid flows were not necessary, but some questions still remain, which is mostly the impact of the non-VFA COD on the enrichment and accumulation, and also strategies on the dry matter concentration. While for the industrial wastewater, we see that the substrate composition fluctuates depending on the residual stream and the process, and also that the fruit juice wastewater achieved a PHA content which was very high, above 60% of the organic dry matter, and that depending on the residual stream, the addition of nutrients is essential to have this process working. Lastly, for the produced PHA and the possible impact on the product properties, we are sure that there are new application possibilities with the PHA that we are producing with our residual streams due to the synthesis of copolymers. So here we can see PHB and PHV from primary sludge, and also the addition of hexanoate with fruit juice or industrial sewage. And I think we'll come to that in a bit with the impact of the PHA composition on the product quality, which Ozzy will talk about. And I think what's mostly important, that PHA is, it has a high potential for substituting PE, which is a very common polymer that's applied today. So I think we're just getting started with the whole process. research questions and challenging for the upscaling. This is just a few, but you can read a lot more about that on the report that will be online on the end, at the end of the month. And I also want to take the opportunity and thank everybody involved in the project, bearing with me during the operation of the pilot plant, and also the support from the whole WOW team. It was a pleasure working with you.
Thank you very much, Lorna, for summarizing quite complicated matter in 15 minutes. That's always a big challenge if you do a lot and you have a lot of nice results. I'm pretty sure there are questions from the audience, at least I hope. See one out, yeah, in the back.
Thank you for your question. Really interesting. I have a couple of questions. The first one is, do you have an idea why there was caproid in the substrate, in some of the substrate, and not in the others? What was the reason for that? And the other question is, do you have something in mind, or are you doing something with the solids that are separated from the fermentation, the flow after fermentation?
Okay, I'll quickly summarize the question.
Perfect.
So the first question was with regards to the fruit juice residual stream that we had some amounts of caproic acid, and if I know why. Not really. I think it really depends on the inflow already. So what you take in the inflow, there was probably something different that day. I don't know exactly what. I mean, to do that, we would probably have to analyze the whole different compounds like carbohydrates, fats, and also protein to then try and work a way around, like why do those end up where? But it might be, for example, that they used another chemical, or that they had a cleaning process in action, or something like this that interferes with the process as well. And this makes it so hard, like, to talk about residual streams, because it's very versatile. Like, not every working day is the same. And I think we see this very well when we look at the two different residual streams from two companies. And I think the more companies you add, the more differences you'll see. The second question was if after the acidification or the fermentation, we use the dry matter for something, because I said that we do a solid liquid separation and then end up with the VFA rich liquid phase. Right now, we're not doing anything with the dry matter that we extract, but definitely there's still some potential in there. And we've been also discussing about this, like how high is the potential of this dry matter, for example, to feed it again into the anaerobic digestion, because even centrifuging the substrate and ending up in a VFA rich liquid, you never get all the liquid out, so you still have some potential there for biogas production, for example.
Thank you.
You're welcome.
Good.
Usually, fruit and juices are characterized by very low pH values due to the wood acid. And did you observe or find any impacts of inhibition on the VFA production by the lower pH values compared to the brewery?
Okay, so the question is, it is usual that the pH of fruit juice residual streams is a lot lower compared to other ones. And if I observed it, and if it might have had an effect on the anaerobic fermentation, definitely very low pH. Like when I popped my pH probe in it the first time, I was like, okay, anybody's living in here. So it was around 4. Sometimes it was below 4, like 3.5. But as I always took an inoculum first, so I always took an inoculum of an anaerobic digester to have the right bacteria in there to decompose or to convert the organic matter into the VFAs. And then I also had pH adjustments, so I always aim for pH around 5 to have the bacteria happy. And then, of course, the process starts to inhibit itself, right? So at a certain amount, if you have acidification, you drop down below a certain pH, then the process starts to inhibit itself. Yeah, but luckily, I didn't have any severe problems. I think one batch was too acidic, and I didn't end up with any pHa after as well. I think you saw some gaps maybe before on the slides. I didn't go into detail about that, but that's what happens. Yeah, if you don't have acids, then you don't have pHa. Thank you.
Question online. Did you evaluate the total pHa production of the plant's wastewater you tested? And any interest in next scale up?
I personally did not, but I think Inka will come to that, like evaluating the overall production capacity that we can achieve using the different residual streams.
Okay, thank you very much, Cora. So now we heard about locations of PHA production. We had a presentation about how to produce PHA, and also a bit about downstream processing. And now, of course, we are very curious what you can do with the products. Well, I'm very happy now that we have Ossi Martika from Lab University of Applied Sciences from Finland, and he will tell us more about the different products that he made from the PHA that was produced at Avans and University of Kaiserslautern.
Hello, good day to you, and as we say in Finnish, noni. So I'll be telling a few things regarding the plastics production, global plastic production overall, and then getting into bioplastics, and just give you some background what we are dealing with, and what is the markets and demand for the plastics currently, and yeah, I'll show you. So the thing is that the plastics produced per annum globally, the volume of the amounts are huge. So 391 million metric tons in 2021, and the production numbers and the consumption figures are rising still. And surprisingly, most of it, well, actually, you might say that 99% of it was fossil-based, because I'd say that most of the, or pretty much all of the recycled post-consumer plastics are fossil-based at the moment. So pretty much all of that is comes from fossilic sources. The bioplastics were like 1.5% of all these, so less than 6 million tons compared to 391 million tons. Yeah, and okay, about the figures, I noticed that there are some interesting things going on, because the Plastics Europe came with the first numbers, and European bioplastics reported that the total bioplastic production capability was 2.2 million tons. But yeah, I don't know what is the fact, but based on this, you can tell that the cup is half full or cup is half empty. So maybe there's huge potential for bioplastics that I'd like to think, and I think all of us within the WOW consortium think. Of course, someone might say that, well, it's insignificant, so who cares about bioplastics? But I think our idea is to increase the production and applications and use of bio-based and also fully biodegradable plastics like PHA. But yet again, the number of all of the bioplastics, or the share of all of the bioplastics, the PHA covers 3.9%, and PLA is the highest one, with the slightly 1/5 of all the production capacity. So I think there's a huge potential for PHA and a very bright future ahead of us. And from the about the PHAs, as mentioned, it's a group of different types of, well, monomers. And, it's a quite versatile group of polymers. So the properties vary, which means that we can also tailor the properties of PHAs. And that is something that we have already learned from Cora, that the properties of PHA vary. And in my opinion, it means that we can also tailor them to suit the different needs and different applications. But anyway, the properties are very well comparable to the most used volume plastics, polyethylene and polypropylene. Only the density of PHAs is higher. But and what about the things that are currently the PHA? What application PHA currently goes to? Well, packaging is the largest. Agriculture and horticulture comes in second. Consumer goods, different items, probably something that I'll show you later on. Coatings, adhesives, and others, they have pretty much the same value, 6,000 tons. So it's pretty much nothing compared to the use of fossil-based plastics. But there are a few interesting things to note. That, for example, PHPV it has been approved for food contact use in Europe already in 1996. So that is one very promising application, field of application, because PHA has very good barrier properties, and it is also very good against UV. So it has very good properties in addition to being combustible. And also, there have been commercial attempts to use PHA. For example, in the 90s in Germany, Vale has made commercial shampoo bottles of PHA, but surprise, surprise, high material costs was the issue that we don't see them anymore. But the reason I wanted to bring this up was that often people ask, or may ask, that okay, if you make something out of PHA, does it biodegrade in your hands? So can you use it in cups? Can you use it in containers? And yes, it has been done already. So it can be used with liquids, but of course it depends on what type of PHA we are working with. So you can choose different kinds of PHAs. Okay, just some ideas where the PHAs are actually used. So in packaging and food industry, there are wrappings, disposable food utensils. So as we know, PHAs typically compostable. And also PHA oligomers can be used as ketone sources in food supplements. So there are quite a lot of interesting applications. Well, in coatings, paper can be made more glossy, give more brightness to it than straight. In textiles, well, you can create fibers from PHA, as the PHA are a set of polyesters. So polyesters are used to create textile fibers and so on. So why not PHA? Of course, well, someone might ask about the cost, and yeah, that might be the issue, but that's the reason we are trying to develop novel and more inexpensive and more environmentally friendly sources and means or methods for creating PHA. And in the construction materials, in the statistic, it was listed as none, but this was one quite interesting that adding PHA in concrete can make it can give it a self-healing properties, so that the crack propagation will stop, and it can grow and stop the seepage through concrete. So, and that is one application in which the PHA quality is not an issue. As you can imagine, that the very low quality PHA, if it's put in concrete, it's fine. It doesn't really matter. It doesn't have to be pure. It doesn't have to have a strong mechanical properties, because it's used as pretty much as a nutrient. And in cosmetics, there are, okay, I'm going up in the value of the application. So skincare products are one. And also PHAs have antioxidant properties, and they can also protect against UV. So they can be used in sunscreens and so on, for example. And especially the medical applications, that's the field where we have a very, very, very high value. Unfortunately, at the moment, we might have some issues using the sewage sludge derived PHA in, but we are working on it. So, but it's very interesting that the PHA, or actually quite a lot of biopolymers are biocompatible. So they can be used as in a different kind of applications inserted inside living bodies. So surgical stables, also heart valves, artificial heart valves, and vascular implants, and so on, so on. So yeah, I say the PHA has quite a lot of quite interesting properties that could be and can be utilized in very, very many different fields of application. Fine. Okay. So about the demo products we have made. So of course we have to take into consideration the fact that the PHA we are using is not purified. It's derived from waste and so on and so on. And also we are trying to figure out how to use it as much as it is. So we should utilize the compostability and other properties it has, taking into account the limitations. So we end up with the different outdoor applications, and I'll be showing them next. And how we produce them, it was via 3D printing. So FDM printing in this case. So we first produce filament and then printed out the demo products. And this is the process pretty much what we did. So on the top right corner, we have an idea of the FDM printer. And on the bottom, it's the pretty much the process we did in order to produce the filament. So the left, we insert the ground PHA into our laboratory extruder, extrude it into the filament, spool it, and then print it. That's pretty much the idea. Okay, it seems easy, but it's always not that easy. But about the application ideas we got, one is the ski pole holder used for cross-country skiing, and they have the tendency of getting lost in the wilds. So we thought that that might be one good product that would utilize the compostability and for which the properties of this waste-derived PHA were sufficient. And also I will find out some numbers of the market sizes. So there are also some markets for these applications. The other one was a fender or mudguard for mountain bikes. And those have all been found that the fenders get easily lost into the wilds. So well, we thought that would be one very good application for compostable bioplastics. And also, for example, globally, for over 44 million bicycles were sold per annum in 2020. So you can think that if a few percent of these fenders are lost every year, there's quite a lot of plastic waste accumulating in the nature. Well, then we have golf tees. So, well, approximately 5 million tees are used annually. So, and also what I found out that there's quite a few options for biodegradable plastic tees in the markets currently. So of course they can get broken or they can be easily lost. So they end up in the nature. And about the 3D printing, it's not about only this for these tees, but also for all of the products. It enables that we can personalize the easily small series of these products. So we can either print person's name or company's name or whatever to these items. So that will actually transform the for example, tea from just a commodity market into a gift market. So that can also create added value. And I think one of the most interesting things that we managed to produce was fishing lures. And okay, this is also related to SEP directive directly. So we know that the fishing lures are lost in lakes, rapids, and so on. And also the issue is it's not just plastics. That's not the only problem, but they can ensnare different kinds of creatures. So they are harmful for quite a lot of different animals and creatures. So in this sense, I think it would be very important to utilize biodegradable and compostable materials if there's a risk that the item ends up in the nature for a while. And it's the idea of the fishing lure. So it is printed in one piece. That is something that you can't do with the, for example, injection molding or whatever. So this is one of the advantages of 3D printing. It's one piece of it. It's flexible, it has joints. And yep, there's the idea, what it looks like. And I also have a short movie here, but let's see. Can I show it? It's just a few seconds. Yeah, that's the idea. It actually swims, it actually works. So, well, that's quite good finding. And about the processing, I can tell you that it wasn't easy material because it has quite narrow processing window. And we were expecting it to be more amorphous-like, but it wasn't. And interestingly, brewery PHA appeared to be more heterogeneous, rubbery. And the one big issue was that these wastewater-derived PHAs had or still have very strong stench. They smell horrible. So that is something that we need to address to begin with, in order to be able to sell these items to all the products to anyone. And well, we have to blend the materials. So this is the ideas of the PHA, WOW PHA printing filaments and their properties compared to polypropylene satinate as a reference. So there are quite a different properties between the PHAs and also, of course, with the PPS. But yeah, you can produce filament that has some properties, and I don't have yet the results from the actual test specimens printed out of these materials because, well, we have 3 weeks left, so no problem. And this is some ideas how it looks like, how the filaments look like. So not bad, but it was interesting. This brownish orange color. So that was also achieved by using this waste derived PHAs. So yep. Yep, that's all. Thanks for everyone.
Thank you very much. It's always nice to see products made from the PHA that we struggled to get for a long time. And if well, the people here, did you bring the example?
I do
today?
have them.
Okay, so if you want to feel and touch, then you're very welcome later to do that.
But be aware of the fishing books. There, I have the actual sample with me.
So there's the book on you. And well, if you're online and you manage to be able to join the Kunststoffenbeurs in Eindhoven soon, then we also will present them over there. So then you also have the opportunity to feel and touch the different materials that we made. Considering time, I only have time for 1, maybe 2 questions for Ossie. And I already see there is one online. Thank you very much, John. How much do we know about PHA degradation in the natural environment?
Well, there are studies indicating that, for example, a bottle made of PHA will completely degrade in the wild. Was it in 6 weeks or something like that? But that, of course, depends on the type of PHA. And of course, if it's very crystalline, that it will be longer. And if it's more amorphous, and so on. That's something that we would very much like to study also.
Yeah, we've done also some research on that at Advance, and indeed it determines, of course, on the environmental conditions. So which environment do you do the degradation? What type of PHA, PHBP it is? But in general, it degrades within 6 to 12 weeks in normal circumstances. But indeed, we need to also look into that a bit.
Yeah, but probably not under snowing. Finnish wind and so
and
yes,
-40, it will take a bit longer, probably. True. I see one question over there.
That's very interesting talk. Just to add to that, one of the problems of durability in nature is the use of it, as you mentioned, in concrete. That could have really serious implications. There's a possibility of breakdown.
Well, about in the in concrete, it doesn't work as a actual structural material, but it's nutrition for bacteria that can fill in the gaps or cracks that form in the concrete.
It's self-healing.
So, yeah, so
self-healing concrete. Yeah, but indeed not for constructional. That's true.
Yeah, it doesn't affect the properties of the concrete as such.
Yeah. Okay. Thank you very much, Steve. Then we go to the next presentation, because as always, when we produce PHA at residual streams, a lot of talk about the economics. So, well, next speaker already was presented in the previous one, so I don't have to introduce you anymore. But Inka will tell a bit more about the economics of PHA production.
Thank you. So I will focus in the presentation on 2 parts of the WOW project. So one on the PHA production from municipal wastewater, where we already get the information about the GIS solutions. And the other part is about the PHA production from industrial streams. Here we want to see which potential we have in the beer and juice industry to produce PHA. So at first, Jeppe already told the use of primary sludge for PHA production, and also Pura shows the results that we get very stable PHA composition with this source. And we show that it's economical feasible to use primary sludge, but we use 2 million population equivalents. And there you see in the figure that we have to combine different wastewater treatment plants. And I want to present two concepts in our report. On the website, you see also different ideas, but I want to focus on two. To transport primary sludge directly to a PHA compounding and processing plant. And another concept is to build PHA enrichment plants directly at the wastewater treatment plant, and then transport the PHA biomass or the PHA enriched biomass with a higher dry solid concentration directly to the wastewater treatment plant. Here in this table, I show the pros and cons of the different concepts. So when you transport primary sludge directly to the central plant, we already see from the GIS results that we need a huge amount of transport kilometers, and we have transport costs. So this is a negative point. So I have only one central, and costs for the plant are lower because you have only one plant, you need less stuff. On the other hand, you see the PHA rich biomass transport. There, of course, you need to transport less sludge, but at each wastewater treatment plant, you need an installation and you need the operational stuff. So this is more negative. And in the evaluation, we see if it's which idea is better, where are the higher costs for the installation. And perhaps one point I want to focus is biogas production. Of course, when you have at one plant, you take the primary sludge away and take it to a central plant, and you have there more biogas production, but on the other plant you have less. And you have also the nitrogen load from the digester has a higher load than to the wastewater treatment plant when you have there a central plant. So here you see the two concepts. I want to show the economical results. On the one hand, you see the process starting with the ferment as a PHA enrichment, which Cora showed in the last presentation, with the fermentation, the separation, and then the enrichment in the two aeration tanks. And then it goes to the extraction plant you see here in the lower part. And in the second, and here you transport primary sludge with 5% dry matter. And in the second concept, you have at each wastewater treatment plant the PHA accumulation, and then you transport the PHA rich biomass with a dry matter content of 3%. We also investigate that we dry it directly at the wastewater treatment plant and have then dry matter of 90%, but this I don't show here in the presentation today. So here you see the results from the GIS solution. So you see the different transport distance from 300,000 to 11,000 kilometers for the two concepts. And here you see the annual costs. We calculate all the capital costs for the installation for the two concepts. So one with the central plant, where you have lower costs for the central installation from 3 million euro per year in comparison to the plant where you have different PHA enrichment plants directly at the wastewater treatment plant. So the costs are higher because you have there more installations, and normally you have a decrease on costs if you have a big plant in comparison to smaller plants. And you see here also the OPEX, excluding transport, that the costs for the concept 2 are higher because of more stuff you need at each treatment plant to operate the enrichment plants. And on the transport side, you see that you have almost 3 million euro per year per transport the primary sludge, because you transport more water than sludge. And but at the end, when you look at the specific costs, it's euro per kilogram PHA, not per tons, unfortunately. So it's about 5 euros to 6 euros for both concepts. And I put the market price for biological or PHA produced from other biological products like wood or which will produce for the production. So this is something about 4 euro per kilogram. So we are a little bit higher with this solutions when we take into account that we have to transport all the things and have bigger or more PHA enrichment plants at different wastewater treatment plants. But it's not so far away. So I think when the prices perhaps rise a little bit, it could be economical feasible also not to look only at one big wastewater treatment plant, or also collect different wastewater streams from other treatment plants. So this is the result for the primary sludge. So now I want to have a look at the PHA production from the beer and juice industry. So we just look for the brewery industry in Northwest Europe, because this is a part of the Interreg project. And so we see here the beer production in this part, and we see Germany not only drinks a lot of beer, but also produces a lot of beer. And so we use this amount of, so it's the beer production from every year, and from the pilot results, I calculate together with Cora and Mitzi the yield. So the PHA production from the brewery industry, we will produce 29 gram PHA per hectoliter beer. And so with the data of the beer production, we can calculate how much PHA can be produced in Northwest Europe. That's about 4,000 tons PHA per year. And it's a little bit the same amount, about the same production when 2 million population equivalent produce primary sludge. When we have a look at the PHA production in the juice industry, so also Germany drinks a lot of juice, but it's only a quarter from the beer. So it's a little bit a pity, because the juice we produce more, as Cora already shows, that the juice concentration is much higher. So the yield is also higher, that we have from the pilots. They show that we could 66 gram PHA produce per hectoliter juice. And so it's a little bit less, although the yield is higher, but because we don't drink enough juice. So it's 2.7 tons PHA per year. So how could we implement PHA enrichment plant at the brewery? So the idea is not to do the extraction at the brewery site. We would only do the PHA enrichment, and the blue boxes on the left side, you see the normal process or the possible process at a brewery site. So the brewery wastewater is first come in a mixing and balancing tank. Then there's sometimes a fermentation tank. This is not always there, but this time at this plant it is. And then you have a UASB reactor or IC reactor for the anaerobic treatment of the brewery waste. And afterwards, you always need the aerobic treatment that you can discharge the effluent to the river. And here you see the additional installation for the PHA enrichment plant. So you need a centrifuge to separate the VFA-rich filtrate from the biomass. And then you have two aeration tanks, one for the biomass selection with a hydraulic retention tank for 2 days, and then a PHA enrichment tank for the with a hydraulic retention tank only for 1 day. And then you have there the PHA enriched biomass. You will separate it again, and then you will transport the rich biomass to a PHA extraction and compounding place, and there you can collect from different places all the PHA rich biomass. So what are here the next steps? So we will make the design for the PHA enrichment plant at 2 production sites, one of the brewery and juice industry, and we will estimate the cost for the installation and also the operation costs, and we'll then include this in the report. And the second thing we like to do is a survey among consumers. So you see here 3 QR codes, one for the consumers. So it would be nice if you will participate at the survey to see how high is the acceptance to use waste streams for the production of PHA, and also for the beer and juice industry separate. So want to get to know how is the waste from these industry parts, and also to get information about the consumption, and also if they would implement such a process at their plant. So.
Thank you very much, Inka. Are there any questions for this presentation? Well, I do have a question. I'm very curious because you didn't show numbers yet of the PHA production price from beer brewery and the juice industry, because you're still not working on that. But your gut feeling, should we continue with both or go for the industrial streams, or what would your advice be?
I think I would go for both, and I think it would be also good to combine both. So sometimes it's always that the brewery is near a wastewater treatment plant. So, and often, as Koba also already showed in the presentation, that they directly put the wastewater to the wastewater treatment plant from the production side. So I think it's a good thing to combine and also have the composition change not so much anymore when we combine both. So I think I would go for both streams, for all 3 streams.
Okay, so it gives a whole new dimension and a whole new GIS exercise, new challenges, I would say. Any other questions? No, any from the audience, John? Okay, then thank you very much, Inka. And then we go to the last presentation of today, because we talked about technology, we talked about economics, but then, well, it's always very good, I think. Well, I never talk to my students about residual streams anymore, about waste. I think it's always a resource to do something with it, but you always have to ask yourself, how sustainable or how circular is it what you are doing? So we also have to keep that in the back of your minds. So that's why within the WOW project, we also looked into the circularity of PHA production. And that's what the last presentation is about from John Gallagher, who is our host today at Trinity College. So I'll give the floor to you, John.
Thank you, Jeppe. So hopefully I'm your favorite presenter, as I am the last of the day. So please bear with me for a short kind of overview of this aspect of the project. It was really enjoyable to work on this project, coming from this life cycle and circularity perspective, because to give context, what will drive this? Hearing earlier this morning in Luxembourg, micropollutants and legislation is driving the need for better treatment. But what would drive potential bioproducts like bioplastics, for example? Well, forthcoming circular economy ISO standards, I think, will be a driving force in Europe, if not internationally, to initiate new ideas around circular products, whether it is bioproducts like this in the bioeconomy, but also in the techno-economy. So from a background, the circular economy ISO standards are the 59,000. They're forthcoming at the end of this year, and they provide a backdrop of the number crunching or the calculations and the evaluation of PHA within this study. So really, very briefly, to introduce the kind of the framework of circular economy standards and how you're measuring or assessing. Essentially, it starts with life cycle principles, but it has evolved around either regenerating, retaining, or adding value. That's what the circular economy aims to achieve. And indeed, there's a framework that thinks about the stakeholders. Earlier, we've heard from speakers talking about who might use the product. That's a very important thing. And some of the values I'll mention earlier reflect that. So there is a framework, and I will go through the process very briefly, but there's complementary methods, forgive the spelling error, around life cycle assessment, which addresses the environmental aspects and is something that has been in existence for a number of years with ISO standards, but also the sustainable development goals. Everything trying to be holistic in terms of how we're connecting to sustainable development. So within this exercise, we wanted to look at the valorization of PHA as a byproduct from primary sludge. But we also wanted to recognize that there's other pathways as well. And the other pathways exist, as mentioned earlier today, and we have decisions to make, perhaps. So we considered the production of PHA cake as a potential replacement of biopolymers, given the huge market potential that was highlighted by Ozzy earlier. But also then we must remember that there's a disruption to biogas production. Not necessarily completely, but there's other pathways. So there's pros and cons. There's pros and cons around energy and lifespan, and we'll try to address that within the study. And also when it comes to the idea of applying biogas or using biogas or creating polymers, the lifespan of PHA may or may not, and has that flexibility to deliver that, while energy, you have to consume energy to make the product, versus biogas where you actually have a producer. So taking the study from earlier, taking the case study of Scotland that you're familiar with from our previous presentation, we took those scenarios, centralized, decentralized, and standalone situation. Each offering different costs to set up, different environmental impacts perhaps in its instrument implementation, but also different social considerations were taken into account in the exercise as well. But the end goal was to try and select a number of metrics or indicators that capture those. I won't get into the detail of this framework, but essentially the system in focus was what we were looking at, PHA cake production. And we recognize that it sits in a sustainable environment, an economic system, a social system, an environmental system. So the current standards are going to be released this year. So we explored what exists in the draft frameworks around flows of resources, and that's key to circular economy. It's about flows of resources, but then taking into account the energy considerations, the economic, and the social, with life cycle assessment offering the environmental perspective as well. So to try and keep it very brief, I framed the findings around 4 different criteria. The first was the resources. And to comments earlier, the lifespan of PHA can compete with traditional polymers, and the results indicate that as a flow of resources. But we must remember, as a circular resource, it's so important that it degrades. The circular economy standards were created so that a replacement product could offer the same quality as its predecessor, PE, as mentioned earlier, as a potential replacement. But PE has its downfalls in terms of environment. So therefore, do we want it to have the same lifespan? And it was so important to hear the different avenues that it can take to help target that. So some of the findings tried to position the PHA as a resource. But I think what was important around the other metrics was to address the economics. Essentially, in the scenario that we looked at to produce a unit or a metric ton of PHA, we can see comparison to PE and to recycled plastics. The costs are still much higher than what the alternatives are. What does the circular economy standards findings allow us to do? It allows us to question how PHA and alternatives can be incentivized, how either the value of 3,000 or 3,600 euro can be brought down in some shape or form, but alternatively, how taxation and other metrics will push the value and costs of PE and recycled plastic up. Perhaps not recycled plastic, but in particular, virgin PE. From a social perspective, having looked at Scotland, we took the previous results and we ensured that the quality of pay, such as taking into consideration living wage, is extremely important. In the context of this study, this was a metric which actually increased the price of production by a proportion. But the social dimension for other resources could look at the quality of life that people have in terms of if it was a finite resource that we were taking into account in a product production, like the chemicals, for example, depending on where they come from, how they're produced, and the people that are responsible for processing those chemicals. So in Scotland's scenario, the cost of ensuring that the people involved in the process would only increase the cost by about 1%. And lastly, the environmental, which I'll come on to in a moment in my subsequent slide, was to ensure that in comparison to biogas, in comparison to the other alternatives, like forgive me, I've gone blank, in terms of biogas and traditional polymers like PE, is it really environmentally a good decision? So just a very summarized, and we will have a much more expanded set of results within the report. We have to take into account as well the infrastructure. So the findings demonstrated that where is the hotspot? Where do we need to focus our attention to try and reduce the cost, but also reduce the environmental impacts? And the yearly PHA production in the center reflects the energy, whether it is heat, electricity, steam, or chemicals, while the embodied represents the infrastructure that must be put in place at a regional level. Transport, actually, given the previous discussion, represents actually a very small amount in this piece of work. So the question is, how do we bring down the environmental impacts of this product? Focusing on energy and other operational inputs is where we need to focus our attention. And so the circular economy findings do highlight the economic costs, but we must recognize in the top possibility of making adjustments to the environmental outcomes, it has a subsequent consequence. More renewable energy might cost more in terms of economic costs. So there's a complex future for bioproducts, but there's a great opportunity to take these results and use that as an influencing factor in making PHA sustainable as we evolve it in its scaling up. So in terms of biogas, that's also the challenge. Biogas is an energy producer, which is extremely valuable to society at the moment. And if we lose part of that by transforming into PHA, the question is, how do we integrate? How do we holistically produce the best of both? And that's kind of a summary of the conclusions. Just to close, I suppose the Scotland case study is a unique scenario, and we need to expand beyond to other regions to explore centralized, decentralized, and indeed standalone. Comments earlier about different, like Eastern Germany, more centralized, would provide more opportunities, perhaps. The standards are new and can be applied to bioproducts, but and what is key is in the future there will be circularity product declaration sheets, a stamp of approval of your product that it's circular in nature. And bioproducts have a huge market opportunity to lead in that space. What is great about circular economy is that we're thinking holistically about sustainability, economics, environmental and social dimensions. And really, the assessment has presented opportunities and indeed barriers, but now is the time that the barriers are presented and addressed to ensure that we create sustainable products in this space going forward. And it can be of value to different stakeholders in the direction that they take going forward. So that concludes my presentation. Thank you to the WOW team. I hope that this kind of sets the tone for where PHA goes. And I'll perhaps hand over to Jappe for any closing questions and to close.
Thank you very much, John, for introducing us to, I think for a lot of us, a whole new topic on circularity, with quite some challenges left, I would say. Well, I already saw Cora had a question, so I'll give the word to you first.
Thank you very much for the insight on the topic. I have a question about the baseline of kind of the frame that you put for the LCA, because I guess that the numbers right now that you use for calculating or the CO2 equivalent what you use were from the current status of the project. So this is kind of the worst case, I would assume. And it would be better when scaling up, right? Because right now it's still a research topic, so you can't really compare to PE production that has been there for years and years, and they are very developed already on this topic.
So to your question, maybe how do we, or are we at a worst case scenario in terms of the findings, in that when we move forward and we move through TRLs and advance that, will we produce a much more environmentally and sustainable product? Would that be, I hope, a good synopsis? The question is yes, in many cases, but perhaps not in all. The environmental impacts are broad. And when it comes to putting infrastructure in place, for example, we're using finite resources. And the more we have to put into that, whether it's the energy sources, renewable energy, is using materials, then we cannot necessarily say that all 17 or multiple metrics behind those three that I presented will actually go down. So we have to look at it holistically. We have to look into the specific areas in which we can make improvements. And yes, we will make improvements, but I always feel that we need this evidence to make that right decision. So like, for example, we are decarbonizing. So that's a very obvious metric that will come down. But how we do that and how every country approaches that is different. I know our colleagues here, for example, in Germany, coal fires are being relit. And so we're not always going in the right direction at present. I hope that we'll make a turn and that the 2030 horizon, which I've been looking at, is kind of a more optimistic goal. But now is the time that we can implement these strategies so that PHA production is, in its essence, sustainable.
Any other questions for John?
Well, I do have a question because you ended your last conclusion was it could be useful for different stakeholders. I'm wondering which stakeholders are you thinking of, and in which way can you elaborate a bit on that?
Well, I think if we go full circle to our first speaker of today, talking about the complexities of a wastewater treatment plant and being net zero, the great map that exists to attain that vision from this morning, to add PHA into it, how does that change the end goal? Biogas production is maybe in place in some facilities. We are diverting and changing what the quantity or perhaps the quality of what returns. So there's consequences that need to be mapped out. And I think if this is part of that conversation, then you achieve win-win-wins. So that's something I think we need to think about. What is everyone trying to get out of this in terms of a bioproduct, a short-lived or something that will last for years? And how would each of those pathways change the requirements that we need to put into the system?
Yeah, which definitely gives a broader perspective than only LCA. Well, I now say only LCA, but then what we do now often right now.
We have a value chain to think of, and it's a lot of stakeholders, and it's having everyone at the table, and community like this represents that.
Yeah. Okay. Thank you. If there's no, thank you very much, John. If there's no questions left. Then I would like to end this session. So I would again like to thank all speakers for presenting the results from the Vale capitalization project today. I think it gave a very nice overview of what we achieved in the past 2 years, and also the challenges we are still facing, and hopefully in future we can work on that. I would like to thank Interreg for financing this project, because it helped us to establish a very nice cooperation between different partners, which I now can call friends, I think, and I hope we can keep on working together in future as well. Well, I mentioned it a couple of times before, we are rounding up projects. Now everyone's awake again, thank you, Cora. So we're rounding off, so not all reports are available yet on our website, but they will be by the end of the month. So if you're interested, please have a look at our website. And we will also, with the people who subscribe for this event, that we will spread the presentations given today. And there will also be the link to the website where you can find more information. So thanks again, and hope to see you again in the future.